All right. Hello, everyone, and welcome to today's installment of Corundum development. So, just to recap on the previous stream that I did a couple days ago, I did a lot of work on basically the new prototype data path for Corundum. So, the plan for today is basically pick up where I left off and put a few, final touches and tweaks and adjustments on the data path to hopefully get it to a state where it's actually usable. Then we're going to do some testing of the HDL code in simulation, and then we're going to load it on the card. Actually, we got to build it, see if it closes timing, see if Vivado reports any issues, load it on the card, and then we'll work our way up to having an actual network device driver that can communicate with it. So for today, what I'm going to be doing is actually connecting this to my main workstation machine, which will make things a little bit easier if we're going to be poking the card with traffic. And we're only running at 10G at the moment, so that interface on the other end only supports 10G, so this should be fine. All right, the fan on here is running right now. It didn't fail this time, so I don't know what happened last time. Must have been a fluke, right? So let's go ahead and switch over to Vivado or the editor, and we'll see what we can accomplish today. All right, let's get cracking on this. So I've done a little bit of cleanup work since the previous stream, mainly just in terms of the top level integration. I think there was some signals that I had not fully connected, so I got that sorted out. And what else did I do? I think that's, I also moved a couple things around. So I went ahead and moved the Corundum top level files into an RTL directory. I also restarted Z, so it actually is listing the files correctly now. So that's definitely a bug that needs to be looked at in Z at some point. Sublime has an option somewhere where you can just have it refresh the file list. With Z, when it gets screwed up, maybe it figures itself out at some point, maybe not. It's not optimal. Far from optimal. Anyway, let's take a look at where we stand with this. So, what I'm going to start out with, actually, is I should do a quick refresher on how a NIC works. And then we'll take a look at the data path that I've been putting together here. Actually, let me switch back to the top view here and grab the piece of paper I had yesterday. All right, yeah. Let's just make sure we're all on the same page here. Where was that piece of paper? Okay. So, how does a NIC work? Let me zoom in here. So, this is actually visible. Okay. So this is what I was talking about yesterday in terms of the process for actually transferring things like Ethernet frames via DMA. Make sure this is at least somewhat visible. The lighting at the moment is not optimal. There's some wires blocking things. Okay. So we have system memory and we have the NIC, and we have to get packets from system memory over to the NIC. And the thing to keep in mind here is that these packets initially are going to be sitting in memory. Now, another thing I should mention as well is that I'm making a bit of a simplifying assumption here in that every packet is going to be sitting inside of one contiguous block in one memory page. In general, that's maybe not going to be the case. The Linux kernel networking stack does have provisions for linearizing packets, but this potentially consumes more CPU, doing internal mem copies and stuff to do that. So to really make something high performance, you got to do scatter gather DMA, where a packet could actually be split across multiple buffers. But for the time being, we're going to set that stuff aside, and we're just going to say one packet is one linear buffer. So what we need to do is get this buffer over to the NIC and out onto the wire. So we talked about the process for doing this and doing this efficiently. The idea is we have to create some additional memory regions in the host, DRAM, and then we point the NIC at these. So the NIC needs to have some basically base address register and length and pointer values associated for each one of these. So there needs to be a producer pointer, a consumer pointer, a base address value, and then probably something indicating how deep this queue can be. It might just be like power of 2 number of elements, something like that. Right, so what's the process for transmitting a packet? What we do in the driver is we take the address and length of the packet, we format that into something called a descriptor that gets written into the transmit queue. The NIC knows the location of the transmit queue, so all we need to do is inform the NIC of the updated producer pointer, and then the NIC can then read that descriptor via DMA and send the packet. Then the NIC generates a completion, which gets written out into the completion ring that we've set aside here. How does the host know that this has taken place? Well, the NIC fires off an interrupt over PCI Express that informs the host that something happened, and it also writes the completion into this ring buffer here. And we discussed the phase tags that are used to indicate which completions in the ring are actually valid. So what the host can do when it receives the interrupt is look at these phase tag bits and determine which completions have been written. Once the driver determines that there's a valid completion here, it can process that and free the buffer such that it can be reused, as well as advance the consumer pointer in the transmit ring to make room for sending more packets. And again, how these phase tag bits work is you initially zero out this buffer, and then as the NIC writes completions in here, those bits get set one at a time. Once we reach the bottom of the buffer and loop around, then the bits get cleared one at a time, so on and so forth. It's a very common technique. A lot of different devices use something very similar. So I know Mellanox NICs do something similar. I know NVMe devices, this is part of the standard. So, you know, it's a pretty straightforward, pretty standard technique for doing this sort of thing. And again, RX is exactly the same as TX. The only difference is which direction we're transferring the data into these buffers. So for TX, we'll put stuff in here. Packets that need to be sent, we'll create descriptors in here, and the NIC will send them. For receive, we'll allocate empty buffers, preload this with empty buffers, and then as packets arrive, the NIC will write them into the buffers and write out completions, and then the driver will hand these off to the stack for processing and refill with empty buffers. So that's kind of the high-level process. What I'm going to be taking a look at today is the actual data path for this, and hopefully we'll get it working on the card. All right. Okay. So let's take a look at the code that I put together last time around here. Get rid of my jacket. Okay. All right. So, starting out at the top level, I have a set of modules here. The top level of this is the core logic with the PCI Express interface logic for ultrascale specifically. So all of the DMA engines and other interface components. So this takes a couple parameters. This will probably be expanded at some point, you know, as more functionality gets added. So on the PCI Express side, we have the main data being transferred here across the 4 sub-channels. The completion traffic, or the completer traffic that's coming from the host or potentially other devices, and the requester traffic that's going towards the host or other devices potentially. And then we have, you know, some flow control related stuff, configuration management, more flow control stuff, interrupts, or MSI interrupts. And then here are the ports for moving Ethernet frames. Let's see, moving on down below that, we have the AXI Lite interface that we're using to access the register space on the NIC. And we have an AXI Lite master module, which takes that CQ and CC interface and it translates it to AXI Lite for accessing the register space. And then below that, we have the actual DMA portion here. So I have the DMA descriptor interfaces. So these are for read descriptors. I mean, okay, so DMA, it's basically just doing a mem copy, right? So you need a source address, a destination address, and a length, and potentially some other ancillary information. So these descriptor interfaces are set up to be pretty generic. They can be used for a bunch of different DMA operations. In this case, for read DMA, the source is going to be a PCI Express address, and the destination is going to be an internal memory address. So that's what's set up here. We got PCIe address on this side, and RAM address on this side. For write, it's interchanged. The source address is RAM, the destination address is PCIe. And potentially, we can also do immediate writes. Although I think in this case, the immediate write is disabled because we're not going to need that. Yeah. And then we also have a length field and a tag value. Tag value is important because you can have multiple transfer requests in flight at the same time, and at least for read operations, they can complete out of order because the PCI TLPs coming back from the host can be interleaved and reordered in various ways. So for the best performance, you have to be able to support reordering, and the way you do that is by using the tags. So I think by default, you can use up to 32 tags, and then if you turn on the extended tag support, you can use up to 256. Although unfortunately, with the way the Xilinx PCIe IP cores are designed, realistically, you can't use more than 64 tags, I think. I need to double check on that. Basically, the completion buffer is too small to support more tags, which is honestly pretty lame, but yeah. So these are for the read and write descriptors, which tell the DMA engine what to do. Then we have this segmented memory interface that's used for actually transferring the data. And then we have, these are statistics connections that are not used right now. And then we have the actual DMA engine here. Oh, I copied that from a test bench, so let me actually rename that. Okay, cool. So this one connects to PCIe, right? It's got the RQ and RC ports here. All of that other stuff that I just talked about connected, right? The read descriptors, write descriptors, and the DMA RAM. Now, one thing you might notice is that I'm passing the same descriptor into two different ports. And this is a technique that I developed a while ago for kind of keeping things organized. The issue is that you might want to connect like the, as far as something like AXI Lite is concerned. Actually, let's take a look at this other module here. AXI Lite, I have one interface that's defined, but I'm connecting it to two different ports. And the reason for that is that you might, at least for AXI Lite, it's divided into 5 subchannels, and you can kind of group that into 2 channels for read and 3 channels for write. So the way I have this interface defined is I have separate mod ports that group the read and the write components together. And that means that you can actually send those to separate modules. So if you have something that's just reading or something that's just writing, you can connect just a part of the interface to that. It would be nice if you could do like a fully hierarchical thing. You could pass the whole thing through, or just the read, or just the write, or just one of the 5 subchannels. But unfortunately, system Verilog interfaces are not sufficiently flexible for that. And this seemed like a pretty good compromise. So I use this technique all over the place. In this case, we have one AXI Lite interface being passed through 2 different mod ports. And then down here, we have a similar setup with the descriptors being split out into the request and status portions of it. So the request basically carries all of the data, and then the status is how you get the tag back when the operation completes, and potentially error information or length. In the case of PCIe DMA, it doesn't give you the length back because it's always going to be the same as what you requested. But for, say, the streaming DMA modules, if you're receiving a packet, you need to know how big that packet is. So that's how you get the packet size back. That comes back as part of the status. And then the RAM interface is going to split between read and write. Over here, we got some configuration stuff, and I'll need to wire up some of these that are not fully fleshed out at this point, like the external tag. That has to come from, so it's like the PCIe IP core for ultra-scale devices. It reports some information, but it doesn't report everything. So, for example, if I go take a look at Where did I put this? Right, so if we take a look at this guy, we can look at exactly what is reported by the PCIe EIP core. I think, are these the only signals I need to look at here? Well, I guess there's okay, I guess there's a handful of things. So some of these things are reporting the status of the link that's coming from the PHY layer stuff, but like the max payload and max read request, these are coming from, I think, the PF0 config space. And then if we go down here, there's also RCB status, which I think also comes from the PF0 config space. OBFF enable, maybe the same sort of thing. These are indicating certain configuration settings, and these are just kind of a convenience thing. Through the configuration management interface, you can read, I think, anything in the config space. So if you need something that's not reported here, or if you need to know what these values are for something other than PF0, then you'd have to go read it. And I have a module lying around somewhere. Let me see if I can remember where that is. Yeah, so I have this module, this PCIe ultrascale config module, which pokes at these signals, and it can read the extended tag setting, as well as the read request size and the payload size. So we drop this in, then we can use that to get the extended tag enable value. But for now, because this is just a prototype, basically, I'm going to leave the extended tag disabled, and then later on, when we're doing performance optimization, we'll go ahead and turn that back on. All right. So where was I? We were looking at I was looking at this. Okay. I'm forgetting what we were looking at a minute ago here. So, going through FPGA core or this one. Getting myself sidetracked here. Oh, right. I was looking at this. Right. Yeah. So we have all of those high-level configurations. So these settings are important to know if you actually want to efficiently utilize the PCIe bus, because the max read request size tells the core how big of a read request you can issue. The max payload size indicates, for the write side, how big of a write it can issue. So the core has to be able to change how it's subdividing a request based on these signals. Now, you actually don't need to connect these. If you don't care about performance, you can leave them at the minimum settings. But this means, I think it's 128 bytes per read request and 128 byte payloads. So if you do enable these, then I think on most modern systems, it's like a 512 byte max read request and 256 byte payload. On some really new stuff, it's 512 for both. Sometimes I've seen the max read request configured for the maximum of 4096. I haven't really played around too much with the, any kind of performance trade-offs between these values. So that might be something to do at some point. Anyway, that's the main configuration of the DMA engine needs. And then we got some status signals and some statistic signals. And then we have the core logic that is device independent. So we'll take a quick look at that. All right, so this is the core logic. We have the control register interface, AXI Lite. We have the DMA connections, right? Read descriptor, write descriptor, and RAM, and then the Ethernet. So this is the AXI stream output for transmit and input for receive, the associated clocks, and also the transmit completion input, which will carry things like timestamps from the Mac. And then all of these are parameterized based on the number of ports. So if we have 1 port or 2 ports or 4 ports or whatever, that should get the job done. All right. I should remove this RAM that I put in for testing purposes. Interestingly enough, the simulation runs just fine with that RAM there. So I guess I need to check to see if that's a Verilator bug, because that would technically be a bunch of multi-driven nets. But maybe Verilator doesn't care about that. Okay. So what I did in the last stream is I went ahead and implemented a very basic AXI Lite register interface. And this one is used to set, the base address register for the TX queue, for the RX queue, for the TX and RX completion queues, as well as some pointer management stuff. So you can write the updated producer pointers, and you can also reset the pointers. This one is mainly in terms of resetting the completion or the consumer pointer. I guess in this case, for the completion queues, it's resetting the producer pointer. Now what I've subsequently realized is that what I need to do is add a couple things to this. So we'll take a look at that in a minute. I need to add probably a bit to enable or disable the register, the queue completely. So we can just disable the queue when we're taking the setup down, and maybe also a better way to handle the resets. And then I also need a way to specify the size of the queue, because right now it will just keep going and going and going, and causing all sorts of problems in the host memory if we're, transferring more than just a couple of packets. So we'll take a look at that in a minute. Actually, I guess it does overflow at some point, but yeah, it's not optimal the way that's built. So I need to rework this a little bit and move some stuff around and add some additional registers. But this code here is just a very simple AXI Lite interface. So we have the write channel here, we have the read channel here, well, for the responses, right? And this, on the right side, it waits for both the address channel and the data channel, and then performs the write when it gets both, and accepts everything and transfers out the read response at the same time. I think technically this is like a violation of the AXI Lite spec, but because I'm just talking to my own code, which doesn't care about the nitty-gritty details of the exact sequencing, then this is fine. In the redirection, we do the same thing. When we get the data, we'll go ahead and accept that and transfer it through. So that's pretty straightforward. I guess for the read data, I could do this differently and just always leave the ready line high, but I'll just leave that for the time being. It doesn't really make that much difference. All right, and now we get to the kind of core of the data path. I've got 4 different modules that I put together here. I have the completion write module, the descriptor read module, the receive path, and the transmit path modules. So all of these are pretty straightforward. They're all doing more or less the same thing, and the core module integrates everything. So we'll take a look at the high level integration first, and then we'll take a look at what the individual modules are doing. So for this to work, we have to have access to the top level, PCIe DMA engine, because we have to read the descriptors, and we have to write the completions, and we have to read the packet data for transmit, and we have to write the packet data for receive. So for read descriptors, we need to split that, as well as the RAM write interface, to support both the let's see, yeah, we need to be able to read the transmit data, and we need to be able to read the descriptors. So all of that goes through here. So I create 2 copies of that interface, and I have to adjust the select width and the tag widths accordingly, because of the way the mux works here. When we're going in one direction, it's going to extend the tag field, because the responses have to be able to be routed back to whoever requested it initially. So if the top level tag field's like 8 bits, then we'll lose a bit as we go down the stack. So it'll be 8 bits at the DMA engine, and then since we have 2 ports here, we're going to do 7 bits to the next level down. And then we have the actual mux module. So this has logic which it multiplexes the descriptors together coming from multiple clients towards the actual DMA module, and then in the other direction it takes the memory writes and it splits them across the internal RAMs. So that's pretty straightforward. And then we do the same thing for the other direction. So we've split everything for the reads, and then we also have to split everything for the writes. Let's see, and now this gets us down to some of the more specific core logic. So both the transmit and the receive path have to be able to get descriptors. So we have descriptor request signals from both of those modules, and these are just very simple strobe. When the transmit module wants a descriptor, it just pulses the descriptor request and then waits for a descriptor from the descriptor read module, and same thing for the receive path. So we have that. And then I have AXI stream interface for descriptors and an AXI stream interface for completions. That's pretty straightforward. And for now, I'm going to make the descriptors and completions to be 16 bytes in size. So both of these are the same size, 16 times 8. Right. So this is a descriptor read module. It accepts, okay, so here's the DMA connections, right? So it has to be able to issue a read request to the PCIe DMA engine, and then it has to accept the data from the PCIe DMA engine as it comes in over the bus. So this will have a little internal memory, which we'll take a look at in a minute. These are the control registers here. So we've got the base address coming in, and the producer pointer and the consumer pointer, and the pointer reset for the transmit queue, and then everything else again for the receive queue. Actually, I guess the consumer pointer is an output, so you can monitor that from the register space if you want. And then we have the descriptor connections here, the descriptor request coming in, and then the descriptor going out. Well, these are actually, I guess, too wide because the mux logic is integrated into the descriptor read module. And then we have the completion write module. This is kind of the converse. Got the DMA connections here, the queue control connections here, and then the completions are accepted here for write out into the host buffer. And then we have the, well, I need to put the MAC connections through async FIFOs because they're in a different clock domain. So this is the FIFO instance for transmit. So we accept the internal AXI stream interface here, and then we produce the AXI stream interface going out. For now, I'm only connecting the first port. So yeah, later on, this will be extended to support multiple ports. And then we get down to the transmit path itself. This is the connection to the DMA engine for reading the data. And then we have the descriptor interface here. We can request a descriptor. We get the descriptor in here. And then we produce the data out here, and the completion is generated here. That's pretty straightforward. And then for receive, we have a similar setup here, where we have the receive FIFO and then the receive data path. So this will accept the data, it'll request a descriptor, we'll get the descriptor in here, then it'll produce the completion. So as you can see, all these modules have kind of similar connections, right? They'll have one connection to the DMA engine, and then you know, a couple of internal connections for handing data around. All right, so let's just take a look at these modules one at a time. So the descriptor, let's follow the transmit path, right? So how does the transmit operation work? Well, the transmit operation is controlled by this state machine that I've put together here. And we start out in, well, actually, let's do a high-level overview of what's in this module first, before I get too far ahead of myself, right? So again, we've got the connections here at the top level. This is this interface I have for the internal DMA engine for actually transferring the data, you know, out the door towards the Ethernet MACs. Then I have the states declared here. Here's that signal for requesting the descriptor, and then here is the state machine that I'll go into in a minute that manages the transmit operations. Then down at the bottom here, I have the little internal RAM. Actually, no, sorry, this is an interface that's used to connect the RAM to the internal DMA engine. This is the RAM, and then this is the internal DMA engine here. So what happens is when this requests the packet data from the DMA engine, the PCIe DMA engine will write it into the RAM here, and then this internal DMA engine will read it here and then send it. So that's relatively straightforward. Yeah. Yes. Oh, right. Yeah. Yeah. So this is the internal control for this. So we have this is the DMA read descriptor going towards the PCIe DMA engine. This is going towards the internal DMA engine, and this is the completion that's ultimately gets sent back to the host. So that's the receive. That's the transmit. The receive is going to be very similar. You can see the structure is basically the same thing. We got this internal interface here. We've got the states. We've got these, the descriptor request signal. We've got the state machine, which we'll take a look at in a minute. We've got the interface for the internal connection here. We've got the internal memory, and we've got the internal DMA engine here. So this one is doing the converse, right? It accepts the receive data from the MAC, it writes it out into the internal memory, and then the PCIe DMA engine can read it out of there and transfer back to the host, right? So that's the transmit and receive paths. We'll talk about the control logic in a minute. And then for completions, it's descriptors and completions, basically the same thing. So the descriptor read module if we look at how this is built down here, it's basically the same thing. Well, we have a demux, but we have the DMA module, which, or we have the RAM here, which accepts the data from the PCI DMA engine, and then the internal DMA here, which reads it out from this RAM, transfers it via AXI stream through a demux out to the either the transmit or the receive paths, depending. So that's basically the same thing that the transmit module is doing, but the state machine is a little bit different here, and we have that demux down at the bottom. And then we'll take a look at the completion write. Again, this is basically the same as the receive module. I'll skip over this state machine for the time being. We'll take a look at that in a minute. This is, again, basically doing the converse, right? We have a multiplexer that brings these together. Here's the AXI stream interface that connects the multiplexer to the downstream components. We have the RAM, or we have the RAM interface here that's used internally. We have the RAM, and then we have the DMA client module here, which does the write internally, right? So we accept the combined completion data from the multiplexer here. We write it out into the internal RAM, and then the PCI DMA engine can read it out of here. Okay, so that's all the data path components. Now let's follow an operation through and see how it works. So we start out here in the transmit path, and in the idle state, we go ahead and fire off this descriptor request pulse. And the idea is that the transmit engine is basically going to continuously try to send a packet. And so it's going to continuously issue requests whenever it's idle. And either that request succeeds and we get a descriptor and we transmit the packet, or that request fails and we basically just go back to idle. So we set this pulse 1, or we set the signal high for 1 cycle. It gets reset on the next cycle here. So it's a single cycle request pulse. And then we wait for the descriptor. So in this case, we wait until we see both tvalid and tready. We set tready high when we're in this state. When we see both of those, then we accept the descriptor and we look at tuser, right? So if tuser is set, then that means that the operation failed. So we go back to idle. Otherwise, we set the request valid on the PCI DMA engine side high, and we go to the read data state. And we also need to process what might be in the descriptor here. So we need to capture the address of the packet and the length of the packet for the DMA engine. And we also need to capture the length of the packet for the internal DMA engine. So that's how we're getting the data out of the descriptor. Once the operation completes on the PCI DMA engine, then we trigger the internal DMA. When that completes, we then go back to idle. We go back to idle and we generate the completion. So that's pretty straightforward. Obviously this is pretty rough. I should probably be adding stuff to make sure that, I don't start things if the completion hasn't been accepted yet or whatever, but just to keep things simple, this should be good enough for some simple functional tests. So you can kind of see how that works. Now, what happens when this signal gets set high, right? Well, that goes over to the descriptor read module, and we'll take a quick look at that, right? So this shows up. We get the descriptor request, and we've got 2 different bits here. And again, this is just kind of quick and dirty. There's I could do this in a better way with a for loop or something to loop across all the bits. But the idea is that this prefers the read side because this prefers the receive side because the transmit side is always attempting to fetch a descriptor. So if we receive a packet, we need to get that packet moving back into the host memory. So that takes priority. So that's why we check bit 1 first, then bit 0. This is where we latch that bit in. So when this is set, then that bit will get set. So if the transmit descriptor request bit is set, then we will go ahead and load up the base address here. Actually, it's not the base address. This would be the address for the actual descriptor, right? So we take the base address and we add the consumer pointer times 16. This will get converted to bit shift, so that's fine. And then this will get sent to the PCI DMA engine. We also go ahead and Oh, what is this? Oh, right. We need to set the tdest value so that the demux works correctly. So this one we set the tdest value to 0. For a read descriptor, we'd set that to 1. We clear this request bit, and then we need to check to see if there was actually anything in the queue. And in this case, if the consumer pointer matches the producer pointer, then the queue is empty. So we jump to the tx descriptor state, and we trigger a transfer of the descriptor. So the descriptor values in this case will be garbage, but we set tuser to 1, indicating that the descriptor is bad and it should be discarded. And then in this case we have so if there actually was something in the queue, then we'll actually be able to read the descriptor. So in this case we'll go to the read descriptor state and we'll fire off the read operation at the PCIe DMA engine level, and we will increment the consumer pointer. So then the next time around, basically this will just run once if there's just one thing in the queue. We move to the read descriptor state, we'll wait until we see the valid, and then we'll trigger the internal DMA and then move to the TX descriptor state. When that gets transferred out, we move back to idle. So it's all in all a pretty straightforward setup. Now in this case, I'm not doing any management of the internal RAM. You'll notice that the destination address from the PCIe side is always set to 0. At least I think I set it to 0. It should be set to 0 here. Ultimately, these are the kinds of things that you would be improving on in the long run. If you're trying to do multiple things in parallel, you would actually have to have multiple slots in the internal memory to store multiple descriptors that you could read in parallel, because it takes some time for the operation to go out over PCIe, to go back to the host, to be fulfilled and make its way all the way back. All right, just looking at the chat now, got a question. How many LUTs would Corundum Micro take? I don't know. We got to find out. I got to build it first. Hopefully we'll have some idea about that today. But the idea with Corundum Micro is it's going to be size optimized. And the legacy version of Corundum, which is going to be much, much larger than Corundum Micro, already fits on the KR260. So yeah, you can run that. You could run that right now. But yeah, eventually with Corundum Micro, that will definitely be able to run on the KR260. Okay, so where was I? Right, so that's, I think, a good description of what's taking place with this particular state machine here for the descriptor read. And then for completion write, I guess I haven't looked at the RX data path yet. All right, well, we'll take a look at completion write first. And this is basically doing, again, the converse, right? In this case, what we're going to do is we're going to go ahead and enable the internal DMA engine first and wait for a, well, I guess in this case, a completion to show up. It's RX desk, but we're waiting for a completion. So that's going to come through there's a mux, right? That takes the completions from both the transmit path and the receive path and merges them together and then sends them to the internal DMA engine. So what we do here is we say, okay, let's receive one. When it shows up, then we will go ahead and write it out to the appropriate location. So how does this work? Well, we need to look at the ID value, because the mux here, this is set up to update the TID value. So the TID value will be set to 0 for transmit operations and 1 for receive operations. So we can look at that to determine where we need to write this thing. If we see the appropriate value for transmit, we'll go ahead and, or if we see the value for transmit, we'll go ahead and write it to the appropriate location in the queue. You can see we're doing the same calculation as before. We take the base address plus the pointer value times the completion size, and then we increment the pointer. If it's for receive, then we do the same thing for receive. So very, very simple. And we do this, actually, now that I'm looking at this could be a problem because we're waiting for this status valid signal. So, okay, let me go ahead and fix that real quick while I'm thinking about it, because that is obviously going to be a bug. All right, so I'll put this here as well. Okay, there we go. So now we only increment those pointers if we actually have the descriptor here. Otherwise that's not so great. Okay. Right. So once the descriptor has been transferred in, then we need to move to write data, I think, right? Thought I tested this thing earlier. Oh, I guess, yeah, all right. Write data. In this RX desk, I'm just gonna go ahead and rename a couple of these things while I'm thinking about it here, right? Oh, wait a second. What was I on? Here we are. Okay. There is no read desk, so get rid of that. Make this 2, and then RX desk. This is going to be RX completion. All right, great. Okay. I think I've already fixed a couple of minor bugs here. Yeah, so that's the completion right. And then for the RX path, we'll take a quick look at that, right? So this is, again, doing sort of the converse of the transmit path. We're going to go ahead and trigger the DMA engine initially, and then move to the RX data state. In here, we will wait until we get a report back from the internal DMA engine indicating that the transfer is complete. So we're going to get the length, right, of what was actually transferred, and we're going to get the oh, I guess we're putting the length in 2 different places, right? So we're putting this both into the completion as well as into the transfer request for PCIe. That's pretty straightforward. When this reports that we have the data, then we move over to, well, then we trigger the internal DMA engine, and we move over to the read descriptor state. Oh wait, oh no, we request a descriptor, right, and we move over to the read descriptor state. So at this point, we're waiting for the descriptor from the descriptor fetch logic. Okay, so when we do get the descriptor, then this block will be hit, and depending on whether or not that was a valid descriptor, we'll either go back to idle, or we will move over to the write data state and trigger the DMA engine to write the data. All right, and then we have the write data state. This one will trigger the completion write and then go back to idle. So, you know, that's pretty straightforward. Oh, and I think there's one other thing I need to do here, right? Because in this case, we need to accept. Okay, so. Okay, yeah, so this is accepting the address, right? So we'll pull the address out of the descriptor, and then this one is going to be potentially pulling the length. So basically what we're going to do is limit the length of the PCIe transfer to the size of the buffer. So if the length that we previously stored is greater than the length in the packet, then we will clip the length to whatever's in the packet. But the problem I'm seeing here at the moment is that if this data is wrong, then this isn't going to work. So what I'm going to actually do is move this inside of here. Okay, so I think that maybe fixes another bug. Okay. So that's more or less how the receive path works. So I'm going to go ahead and run the simulation wherever I had that. I have a lot of stuff open right now. Okay, there we go. So this was the simulation that I ran before, and I guess I can take a quick look at the simulation Python script here that I wrote last time around. So what this does is it basically goes through all the steps that I talked about just a minute ago on paper, right? So this allocates a region of memory for the receive queue, for the receive completion queue, for the transmit queue, and for the transmit completion queue. And it goes ahead and writes all of those registers that I just mentioned a couple minutes ago, right? It sets the base addresses and the producer pointers, although everything starts out at 0. And then we actually attempt to send a packet, right? So we allocate a receive buffer, and we increment the producer pointer and write that into the appropriate register. And then we do the same thing with a transmit buffer, right? So I go ahead and create the buffer, or I allocate the buffer. I put some test data in it. Right, there's the actual write to the buffer, and I create a descriptor, right? So this one has the length of the packet and the address of the packet. And then we increment the producer pointer and write that to the appropriate register. And then I have to actually turn that packet around. So I wait for the packet to show up, I turn around and send it back into the design, and we wait a while and we see if it shows up in the receive buffer. So I'm going to go ahead and hit build here, and well, this is going to take a couple minutes to build, but what we can do is take a look at the simulation trace from the last time I ran this, and then we'll see when this thing completes if anything has changed. So we can see right here, these are all of the ultrascale format TLPs that get sent. So we can see the addresses, right? If I look at this here, what is the sequence, right? I do 200, 204, 208, 20C. Well, we do 200, 204, 208, 20C, and we can see the values that get written in here. So like, here's the base address, here's the next one, so on and so forth. All of those look reasonable. So this is doing all of the initial setup, and then we have to wait for the links to be operational so we can actually send and receive data. And then we dump out, okay, and then let me see. We're going to set up the receive buffer and the transmit buffer, and I do a hex dump on the receive and transmit queue. So this dumps out the descriptor. So we can see here's the length of the buffer and the address of the buffer, and then again the length of the data that we want to send and the address of that buffer. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, that looks right. Okay. Yeah, so we have that, and then we can actually see, okay, so here are the two writes to update the pointers, right? So we've got 208 and 108, incrementing the pointers to 1, and then we can see the design actually running. So we can see the RQ frame. This will be coming from the DMA engine to read the descriptor. So here's the address. It's trying to read 4 D words. So here we go, length 4. And here's the data going back, right? So we can see here that this corresponds to this transmit descriptor here, right? We've got the F, we've got the 1005, right? So that goes to the card. Then we see another request here, right? This one is for actually less data because our string is pretty short, right? We can see length 4, so it's 4 D words, but then the byte enables indicate that we're actually reading 1 less byte. So this is for 15 bytes. And you can also see that the tags are different here, right? So this was read with tag 0, this is read with tag 1, and then we have another read down here with tag 2. So that's the memory read for the packet data. Now we can see here that looks like some data, and then what pops out of the transmit port, right? That says receive because the module we have connected is acting as a receiver. And hey, there is the data that we wanted to send. Now it's 0 padded as appropriate with the FCS added by the Mac. So we go ahead and turn that around. We send the exact same thing back in, and we get the receive side comes to life now, right? We get RxRQ frame. Oh, I think this might be in relation to one of the bugs that I fixed here. I think this is a, yes, memory write. So this is completely bogus. This would be for the completion for the transmit operation, I think. Then we get a memory read. This is going to be from the receive queue, right? And then here is the associated data that appears to match the receive descriptor here. And then we have the memory write here that hits the actual buffer that we set aside for the receive packet. And then that's a hex dump of that buffer. So the data ended up where it was supposed to end up. There's just a couple little odds and ends that we need to sort out here. Yeah, okay, so I ran it again, and yeah, the problem, one of the problems that I noticed is that when it did this write to the buffer, it was length 4 byte enable F7. So this length is wrong because it doesn't match the padded frame. It matches this length here. So something got mixed up at some point. It looks like it limited the length to whatever was in the transmit descriptor, which is not correct. After fixing some stuff, okay, yeah, this looks right. So this write operation, all right, so there's a couple things to look at. So after we turn the packet around, we can see a write. Okay, there we go. this one looks like it's probably hitting the receive completion queue, or the transmit completion queue rather, right? At 300, is that right? I think that's right. Let me see here. So 300, yeah, the RX or the TX completion queue. Yeah, so this looks correct now because the address is not totally insane. Yeah, so this write looks correct. So we've successfully written the transmit completion out into the host memory. And then we got the same thing going on here, right, for receive. So we have a write of the actual packet data, and I guess I didn't wait long enough to see the completion get written out as well. But we can see length 15, which I think corresponds to the actual padded length of the frame. So we can see over here, there's the packet data followed by a bunch of zeros. So that looks correct, and we can see the data here. So that's looking pretty good. So what I need to do next here is I need to take a look at those registers and see if I can clean things up a little bit, because I need to do, what do I need to do, right? I need to add enable bits so I can enable and disable the queues. And I need to add the ability to set the size of the queue. Because if we look at how like the descriptor read and completion write logic works, this could end up being quite a large number, right? And this is just going to keep growing until this rolls over. So unless you allocate a very large block of memory, this is not optimal. Although this actually, I think, would be probably good enough to do a quick test and see if we can basically do the same thing that we've done in the test bench. So it's probably a good opportunity to do a test build and see what happens here. So let me see if I have, yeah, I guess this is the Vivado project I was using before. All right, so we're just going to fire off make, and we're going to see how badly this fails, and then we'll go from there. There's a couple other things I need to do. So while this is building, I guess I'm going to take a look at what needs to be done from the standpoint of interrupts, because we have the logic now to basically to run the complete operation, to transmit a packet and receive it and get that back into the buffer. But there's nothing right now about actually firing off an interrupt. That's important because we have to be able to, you know, wake up the driver and have it go look at the receive queues and hand stuff off to the operating system on the receive path. So let me think about this here. I guess what we're going to do is have the completion write module generate an interrupt. So we can add an output here. This is going to be output, if I can type correctly. This is going to be IRQ. That's just going to be 1 bit wide. Okay, so I can copy that and go down here. All right, and then I can assign that here. Okay, and then down here I can do the same thing. That's just going to be a single pulse, so that keeps things simple. And then in the write data, yeah, so when this is valid, then we go ahead and fire off the IRQ. Okay, did I? Yeah, all right, that looks good. Actually, I guess I should put a couple other things down here in reset to make sure everything gets reset properly. Always important to make sure that the resets are covering all of the correct signals. One thing that I like doing is not resetting like every single signal in the entire design, because if something is qualified by like a valid signal, then as long as you reset the valid signal, you don't need to reset any of the, you know, covered signals. All right, so that will provide an interrupt output, and then we need to get this interrupt output back to the top level. So take that, and what am I going to do with that? That's going to go over here for now. I'll just put it randomly over here. Okay, and then we'll go ahead and connect this to the completion write module. Just down here. Okay, great. So that's there. Now what I need to do is get that IRQ signal connected to the PCIe 4. Think about how I'm going to do that. So I think what I need to do is a couple of things. Something is slowing down on Vivado, eating up a lot of memory. Okay. Something is not working as I was hoping it would. I think Vivado is eating up a lot of memory and CPU on my development machine here. So hopefully this is not causing any major disruptions on the stream. Anyway, I guess I'm just gonna have to keep going and we'll see. Alright, so wire 2100 MSI IRQ. And then what I need to pull in here is there is a module that I have here for interfacing with the PCIe IP core for actually generating the MSI interrupt, because you need to do a little bit of additional work for this to work correctly. YouTube seems to be complaining about something about the stream quality, so I think this is probably a result of Vivado using up too much memory and CPU on here. Yeah, this wasn't an issue yesterday, so, or not yesterday, but on Sunday, so hopefully this doesn't get too much worse. Anyway, I'll just keep chugging along for now, and then we'll see. Oops. That didn't copy what I wanted to copy. Alright, so I'll copy this. Alright, where were we? PCIe US. Okay, there we go. Alright, so MSI count. MSI count. Now, I don't need 32 MSIs, but just to keep things simple, I need to go ahead and make all these connections really quick here. So I do that, and then this is going to be the MSI IRQ signal. Alright, and then this one, I'm going to set this equal to 32 prime IRQ. Right, okay. And did I connect that at the bottom? Right, I have to add the IRQ signal here. Okay, that looks reasonable. That gets tabbed in, and then I need to go ahead and make all of these connections as well. And I think this is basically just going to be a copy and paste from... Where should I go for that? Yeah, I guess I can go over to here. Let's see if that works. Oops, not that file, this one. Okay. All right, so let's see if that works. If I did everything correctly. Oh, did I actually set up the interrupts here? No, I didn't fire off anything to set up the interrupts. All right, let me take a look here and make sure that's enabled. Right, allocate IRQ vectors. Okay, I think that should set up the interrupts. Oh, yeah, okay, now that should be correct. Let me just see PCIe core configuration. Do I have MSI enabled? Yes, I have it enabled with 32 vectors, so that should be correct. All right. Oh. Uh-oh. PCIe US. Extraneous comma. Oh, and then I also need to add over here, I need to add one more thing. Okay, right, I need to go here and I need to add PCI US MSI.SV. Okay. All right, let's see if Verilator's happy with that. Oh, all right, something is unhappy. VF enable. I need to fix a couple of things here. Great. One moment. This should only take a minute, I think. This is, I think, the first time I've tried to use this module, and it has a couple of minor issues that need to be fixed. Let's see. So MSI enable, so that's line 114. I need to pull out bit 0. And I think the rest of these are maybe correct here. Okay, so function number generates 8 bits. Wait, is it, how many bits is the ST tag? I think that seems weird. Let me check the documentation for that. EPH type ST tag. Yeah, that should be 8 bits. Oops. Alright, so that should be 7. Okay. And then this is talking about the MSI function number. Alright, so that's full 8 bits as well. Pending status function number. Okay. Well, let's see what that does if I rerun it. Okay, so that fixed a couple of those problems. Oh, let's see. So I got to do a couple more things here. Line 71. I'm just going to make all these unsized. Yeah, this module has to work for both UltraScale and UltraScale Plus, so that does complicate a couple things in terms of the sizing. I may need to do some cleanup work a little bit later. So MSI select, still have a problem, and pending status function num, we still have a problem. All right, well, one step at a time. And VF enable. Okay, so I need to go ahead and just add that pin. All right, and I think for the time being, I'm just gonna bypass these errors by temporarily turning off the linter. I can deal with this. I can deal with this later and properly fix this later. Okay, let's see if this does what it's supposed to do. When this builds, we should be getting a message at some point about the interrupt being fired off. Okay, so this one failed. It probably failed because I was in the middle of editing some stuff. So, oh, all right. Yeah, so this is missing the file. So I'll go ahead and rebuild that. Okay. All right, so we'll let this thing build. All right. Once this is built, then the idea is to take the driver that we were working on before and see if we can run basically the same test that we're doing in the Python and do that in the driver and make sure that it does what it's supposed to do, right? Can we send a packet? Can we receive a packet? Then the next piece is going to be, okay, can we connect this up to the Linux kernel networking stack? All right, so Vivado is still getting itself figured out here. Okay. I'm going to start actually by, now let me think here. What is going to be the most straightforward mechanism for doing this here? Actually, I probably should go ahead and add the queue enable bits first before we test this out in the hardware, because without those bits, we could run into problems if the design does something silly if we reload the driver a few times. So, all right, let's take a look at that. This should be pretty straightforward. I need to add a couple of different things. I need to add enable bits for all of these, right? So for every single one of these queues, we need to add an enable bit alongside the base address. Oops. Okay, and then I also need a queue size. And how many bits does that need to be? Well, the pointers are 16 bits, so the size is going to be the log 2 of that, because what I'm going to do is shift a bit mask. So I think I need 4 bits, right? Because the max value you can specify there is 16. Oh, what happened here? All right, let me, all right. Do the edit correctly. All right, so this is going to be 3 to 0, because if the pointers are 16 bits wide, the maximum I want is 15 bits. Okay, that makes sense. Okay, great. So I have enable and size that need to be added to all of these. That shouldn't be a big deal. All right, so let's go ahead and hit every single one of these. This is not a big deal here. All right, so enable. And this is going to be, I did 3 to 0, and then enable is just 1 bit. Great. And I think I can also get rid of the pointer reset values as well, because when you disable it, that will reset the pointer. Okay. Yeah, okay. So this is going to be, I'll do en. If it's not enabled, then I do that. If this is not enabled, then again, I do that. Okay, cool. And then I also need to do, so let me think about this here. So the thing is, if it is enabled, all right, so this is going to move state right data. Okay, so what I'm going to do now is I'm going to put if, so if the TX completion queue is enabled, then we can move to the right data state. Otherwise, we drop the completion and return to idle. Okay, great. And then I need to do the same thing here, but for the RxCQ. And I will, oh, and then all of this needs to go inside of this as well. Yeah, okay, cool. And I might as well go ahead and also, well, yeah, that's fine, I think. Okay, great. All right, so then this goes away. Is that right? Yeah, that looks good. Okay, so you can see how this works, right? When we read the descriptor into the internal memory, when that operation completes, right, we get the status. Well, we would get status valid here. You might be wondering why I'm nesting these if statements in a weird way. This is basically an optimization technique where I don't want this status valid signal to be a clock enable input or a driver of a mux or whatever when it's not actually necessary. So like, I don't really care if I temporarily pull in an address that isn't helpful, but it is a problem if the pointer value gets incremented when it's not supposed to be. So I got to wait for this to be valid and for the queue to be enabled to actually trigger the DMA operation. But I can absolutely latch in the address when none of these are true. So that's fine. Okay. So this, I think, is going to work fine for the completions. Now for the descriptors, I got to do the same sort of thing. So this is going to be TXQ enable and RXQ enable. When it's not enabled, oops, when it's not enabled, then I will do that. Let me actually make sure. Yeah, I did that correctly here. Okay. And oh, let me actually make sure I have the correct registers over here. So I got to add enable and I got to add size. I also got to fix the size thing too, right? So that's going to be 3 bits, and then enable here. That's, there we go. Okay, great. Getting back to the code. All right. So if the queue is empty, or if the RX queue is not enabled, then we do that. And we do the same thing for the TXQ. I think that's all we need to do, right? That, I think, looks correct. Because if it's not enabled, then we're going to skip straight to the TX desk where we send an invalid descriptor because the queue is disabled. All right, perfect. Okay, that looks pretty good. That was a little bit simpler than I thought. All right, so go ahead and save that. We'll save that. All right, and then what is next then? I need to go ahead and make the connections over here to those modules. Okay, just looking at the simulation ran again, it looks like. So I think everything then is working correctly. Yeah, oh, here we go. We have issue MSI interrupt index 0. So this did actually fire off the MSI interrupt. Now the test bench I didn't register any sort of handler to handle the interrupt, but it did fire it off from the root complex model. So that's a good start. Okay, so that means I think I have all the interrupt related stuff hooked up correctly. Now what I need to do is go back to, oh, I need to do 2 things, right? I need to go ahead and make the connections here. Did I remove the, make sure I remove those signals here? Yeah, so I didn't remove the pointer reset signals yet. I'm going to go ahead and get rid of those. Okay. And I think they're also removed here. Okay, great. So that looks good. And then I'm going to go over here and we're going to get rid of pointer reset. Yep. And then base address. Oops. That. Well, I guess that actually would have been fine. But anyway, all right. So we'll do that. And then this is going to be enable. And this will be enable. And this is going to be size. Going to be size as well. Okay, great. I need to implement the size function. So all right, next I'll do that in a sec. All right, so we'll remove that. Then base address, we have enable and enable. Oops, to duplicate. Okay, then size. There we go. All right, so we have enable, we have size, we have the base address, we have the producer pointer here. We got the same sort of setup here. All right, now let me actually fix the register layout. And let me go ahead and get rid of the pointer resets here. Bing, bing, bing. Rid of that. Okay, perfect. All right, so what I'm going to do, actually separate this out so we can see all the individual groups. All right, so what I'm going to do is put the base address registers second. so this is going to be 8 and C, and 8 and C, 8 and C, 8 and C. This is for writing. So the producer pointer, I'm going to put that on 4, and pointer reset, I got to fix that. So this is going to be on 4, and then that'll be rewritten in a minute. And this, yeah, that's a pointer reset, and that's a pointer reset. Okay, great. So what we're actually going to do here is we're going to do the enable. Well, actually, I guess there's a couple things I need to do, right? So we're going to do enable, and I'm going to pull this out of bit 0. Actually, why did I cast this 16? All right, let me do 15 to 0. There we go. That's a little bit better. Instead of 16, casting. All right, and then I will go ahead and do the same thing here for RX. All right, so that's 2, and that's RxQ enable, and same thing here. Actually, I can do this differently here. All right, so this is going to be enable. Okay, cool. And I'm going to go ahead and get rid of these pointer resets here. And were there more down here? No. Okay, that looks good. All right, so we have the enable connection set up. Now what I need to do is add all of the size registers. So we do begin. What happened? Something didn't work the way I wanted it to. Okay. Okay. Okay, that looks better. All right. Still Z is having something in wrong. Okay. There we go. All right. So then I can set size, and I can edit all these at the same time here, which is great. And the size, where am I going to put that? I guess I can put this starting at bit 16, 17, 18, 19. Yeah, okay. There we go. I think that is going to work. Oops. Not size en reg. What happened? Okay. All right. That looks better. So we have enable, we have size, producer pointer, base address, base address. Okay, that looks good. Now let's do the same thing down here. I'll take all the base address stuff. All right, I got to do this more carefully, so I'll do that, and then I will do that here. All right, great. All right, so the base address registers, that's going to be 8 and C, C, and then 8 and C, and 8 and C, and again 8 and C, and then let's see. So the producer pointer, that's going to be 4, right? The producer and the consumer pointer, I need to clean that up real quick here. All right, so the producer and the consumer pointer, the producer pointer, I'm going to put that in the low order bits, and then in the high order bits, that will be this will be 16 to 31. So we can read both of those pointers at the same time, right? Yeah, okay, perfect. So I'll copy that, and I will go ahead and paste this here, and this one will be for this needs to be 104, 104, and this is for the RxQ, and the CQ. Okay, there we go. And then we can do all of the reads, and that's what's the easiest way to do that? All right, I'll just have to copy and paste it. That's fine. So we'll start at 400, and then I need to flip these around. Okay, great. And this is going to be SAXIL R data reg. There we go. So we can go ahead and read those bits. Perfect. And then I can copy that for all of these. It'll be 300. And this is going to be the TXCQ. And then this will be 200. And the RxQ. And finally, we go up here with the for the TXQ. And that's at 100. Okay. I think I got all that correct now. Now I need to go update the Python code again. But this is looking reasonable. Oh, I need to fix the size. Right. So now that I've added the registers, I now need to implement the actual size register. Let me see what Vivado is doing here. Why is it still complaining about not being able to find the PCI US MSI file? Ah, what happened? So that is specified. Did that actually recreate the project? I thought it did. Ah, all right. Let's try that again and actually properly rebuild it. I guess touching the file was not enough. Gotta delete it and force it to recreate it. Now it's running the create project, so that should actually do something useful this time. So let me run the simulation again. The simulation is not going to work properly because I need to fix the registers in Python. But the question is Verilator going to start the build process? Okay, so it looked like Verilator was actually happy with that. So great. Oh, I still need to implement size. All right, I'll do that in a minute. We go ahead and reorder these. Got to make the same set of changes basically that I did before. So this is 8 and C. This is 0. I write, well, I need to write, so I'm going to write 1 to enable it, and I also need to write the size. What is the size? So let's think about this. If it's 4096 entries, so 4096 over 16 is 256 entries. So 2 to the 8, I guess. So I write 8. All right, so I need to write 8. Yeah, all right, I think that will be correct. So you can see we set the size and we set enable. Simple. Great, so I do that, and then the producer pointer here. Let's see, so this is 8 and C, and for 4 I need to write, I'm just going to write 0, and for this one I'll write that. Okay, so we'll do the same thing up here. All right, and this is 2 and 2 and a 1, 148C, and then again I need to write that same value here. All right, so this will be 408 and C. Okay, great. So what this does is it enables all the queues, it sets all the sizes, and it clears all the pointers. So now we're ready to go. Now when we update the actual pointers, I just need to update this. So this is going to be 204 and 104, right? Yeah, okay. I think that's going to be correct. All right, Verilator is still building, so as soon as that's done, then we'll see if this thing runs. And then once that's done, then we should be in a good position to actually make an attempt to run this on the card. So, okay. I think yeah, I might need a different approach for that. This is the downside of trying to stream off of the same machine you're running Vivado on. I don't remember this being as big of an issue in the past, but... Alright, well, I just killed something. We'll see if that does anything. Hopefully I didn't kill something important. I think that freed up some memory. Okay. Alright, so the simulation went ahead and completed at this point. And let me see here. So we are writing... I think we're writing to the correct... Yeah, okay, so this is the new setup, right? You can see that we are hitting... What is this one? 3000... What am I looking at here then? So this one is writing to 308, and why did it write 3000 to that? 308. Oh, alright, so I guess that's just one of the addresses. I've always been writing those addresses? I probably. Yeah, okay. Something seems strange here. Alright, so this was C000, then 1003,000. Yeah, I'm not sure why it's a different address that time. That doesn't make sense, but it does look like this did what it was supposed to do. So we can see the packet going, we can see the packet coming, we can see the interrupt getting fired off, and we can see the completion right. So, okay. Oh, so what? So I still need to implement the ring size, right? And I need to implement the size mask. All right. But I think I can probably test this on the FPGA in the meantime, assuming Vivado actually builds this without any major issues. So it looks like it's running synth right now on the IP cores. So hopefully it'll build in a couple of minutes here. All right, let me take a look at the kernel module for now. So the one that I put together before was just a very simple test module. And I think what I'm going to go ahead and do is, should I rename this? Get rid of that. Get rid of that. Okay. Yeah, I'm going to go ahead and rename this to, Corundum, basically, and then we'll start with that. Let me clean this. All right. We're going to try to make this a slightly more professional driver than the last time around. So I'm going to have to add probably a handful of files to this to get something usable. So we have the main, and we go pull up the reference driver that I've been looking at here. So I'll create a header file here. Oh wait, not that. What am I talking about? and if. All right, there we go. And then in this case, what do I need to do here? I need to transfer over some of the includes, I think, right? So kernel PCIe. Yeah, all right. So I'll go ahead and transfer both of these over here for now. And then for the main module, or for the main.c file, I'm going to go ahead and, yeah, we'll put the yeah, there we go, perfect. And then I can get rid of both of those. Great. Okay. All right, and then what I need to do is I need to transfer over a couple of, I need to create a couple defines as well. So let me go back to here, and I'm going to go ahead and create a define driver name. All right. And then I also need to update this to, let me see here. There's a particular way to do this for, all right, so this is cn.o, and then I need cndy. There we go. All right, so for pulling in multiple files, there's a particular way that this has to be structured. I think this will work. What I should do before I get too much further along is to do a rebuild, and we'll see how this works here. So I'm going to run make on the kernel module, and let's see if this blows up in my face. Hey, okay, that actually built. Perfect. All right. So by creating this define for the driver name, then any place where I need to use the driver name, I can use that instead. So there were a couple of spots where the test was to, does this need to be changed? Yeah, okay, so, oh wait, no, that's not what I was looking at. This is the PCI driver structure. Yeah, okay, so I can go ahead and put that here, and then I think it was also the reserve regions call, perhaps, that needed that. Yeah, or request regions. Yeah, perfect, okay. And then test, I can start renaming all of these to all right. That looks pretty good, and I think there was another defined add over here. Maybe not. Okay. Set module author. All right, and oh, there's also a driver version. Well, I can deal with that later. Okay, great. So with this setup, I should be able to start adding. I should be able to start bringing back this test code. So I'm going to start by commenting this out because I don't want to start writing to random registers. And here, that being slightly annoying. Okay, let me check on Vivado here. Vivado failed. What happened? Still? What happened? This did create that, Alright, now I need to go debug my build setup. This is annoying. Alright, maybe it didn't actually regenerate that script the way it was supposed to. Okay, now it's in there. How many times does it take to make this work? I should have done a make clean. I didn't do a make clean. That would have solved the problem. Alright, well, whatever. Alright. Vivado is starting up again. That will take a minute. Hopefully, like ninth time's the charm, you know? Okay. Great. So let me take a look at the kernel module again and see about getting this Python code transferred over. So the idea is that we're just going to basically do exactly the same thing that we're doing in the Python in the device driver, and we'll see how that works. So again, this is just a really quick first pass test just to see what happens. And actually, I guess another thing that I might need to do is use a loopback module. Let me see if I have a loopback lying around. Okay, there we go. I found a loopback module. Let me get this thing installed. Alright, so what I'm doing now is I'm just going to put a loopback into this card, and we will use that for the initial test instead of trying to loop another device into the picture here. So I'll take this cable out. It's really stiff for some reason. And then I will insert this loopback. So, you know, if you're not familiar with the loopback, there's really not much to it. It's a... is camera going to focus? There we go. Yeah, so this is just looks like an SFP module, except it doesn't actually have a cable coming out of it, or fiber or anything else. It's just a very bare module. So we'll insert that in here, and hopefully that'll work. Okay, great. Okay, so once we get that set up, then we'll actually be able to turn the packet back around on the NIC and send it back. So what I'm going to do here is I'm basically going to copy all of the Python code, and we're going to transfer that over, and we're going to run all of this effectively, but the C version on probe, and it will send and receive a single packet. Once that works, the next step is to actually connect it up to the operating system. So, one step at a time. Where's that kernel module? All right. I'm going to go ahead and paste all of this in for now. Trying to think about what's the best way to handle this, because we need several different memory regions for this to work, and I'm trying to think if I want to do one allocation and just kind of slice and dice it, or make one bigger allocate, or make a bunch of smaller allocations. I think I'm just going to go ahead and make one big allocation. Let me actually check on Vivado really quick and see if it's made any progress here. Okay, it's still running the synthesis of the IP cores and such, so that will take a couple minutes to finish up, I think. All right, where was I? So in the driver, what have we done so far? We've enabled the device. We've set the master bit so we can do DMA. We've requested the bar regions. We've read the resource length of bar 0 and mapped bar 0 so we can use bar 0. We've also fired off the allocate IRQ vectors, so all of that looks good at this point. So what I need to do next is I need to allocate a block of memory. Right, okay, so let me actually move this structure over to the header file. And then I can go ahead and add some additional stuff to this. So let's see, where was this structure defined in this example driver that I'm looking at here? I guess there was actually an associated header file with that, right? Yeah, okay. So for the DMA buffer, there's a couple of things we need to do. I'm going to go ahead and create a, if I can type, size t for the DMA region length, and then a void pointer for the DMA region. And this is pointing to the kernel virtual address that gets allocated, and then DMA ADDRT. This is a DMA region ADDR. Okay, great. And I'm also going to do int IRQ count, which we can use for making sure that the interrupt is actually getting fired off. All right, great. So I need these variables for when I call DMA alloc coherent, which is the function that you use to get a fully DMA addressable block of memory. All right, let me see here. We're going to allocate the DMA addressable memory. And the way we do that is we do, actually I've been using T, but I'm going to rename that to something else. But I do CDev instead of. Okay, great. That looks good. That's a little bit better. Okay. All right, so we're going to do CDev DMA region length, and we're going to set that to, I guess it doesn't need to be very big, so I'll just do 16K for now. If we need to make that bigger, that's just one line we can change here. All right, so CDev DMA region, and this is going to be set to DMA alloc coherent, and this is, we're using dev because it has to be associated with a device, and then we're going to use the DMA region length that we specified here. Right, and then we also need the DMA region address, and we pass that as a pointer, and then it's GFP kernel and GFP 0. So we want the kernel to go ahead and zero that out for us. All right, now if this didn't work, then we need to return an error. And then we go to fail DMA alloc. All right. And this is going to be here for fail DMA alloc. All right, great. Perfect. And now what I need to do is make sure that we are deallocating this at the end, because if we don't free the memory, then that's memory leak, right? So that's not ideal. All right, so I do DMA free coherent dev we CDev DMA region length dev DMA region CDev DMA region address. So a bunch of stuff we got to keep track of for this to work. And I'm also going to go ahead and put this up here for if we're adding any other related code. If there's we fail later on, we'll also have to free the memory. Pretty straightforward. Yeah, I think this is all correct. It's all looking correct for now. Okay. So while Vivado is running here, I'm just going to continue translating this until, oh no, it crashed again. What happened? Not resolve hierarchical name. All right, so I think something else may have failed before that. Maybe? All right, I guess I need to take a look at this then. Where is this problem? This is in the DMA desk mux. Oh, okay. No, I think I might know what happened. DMA desk mux. I think I've run into another another verilator bug. Yep. So these actually, this should be a syntax error as in verilator, but for some reason it isn't. All right. Yeah, if Vivado complains about something that verilator doesn't complain about, it probably means that verilator is it should be complaining about that. So yeah, whenever you're pulling parameter values out of an interface array, you have to dereference the array. Verilator doesn't complain if you don't do that, but Vivado is not happy. So easy fix, easy fix. Always good when it's an easy fix. All right. So while that's building, let's go back to the driver here. While it's building, well, we'll see if it builds or not. But while Vivado is grinding away at stuff, yeah. Okay, so what I'm going to do for the time being is I'm just going to define everything locally, and we're going to make sure that the hardware is doing something useful. Once it looks reasonable, then it'll be, the next step will be to kind of refactor it into something that can actually be connected to the operating system as a network device. So I need to go ahead and define all these pointers then. So U16 RxQ prod U16 RxQ cons. I got to do this again for the TX queues, and then for the TX completion queues, or RX and TX, or everything for the completion queues. All right, so set all these to 0. Great. Yeah, for now I'm just going to start using, random stuff, but the idea is that we can improve on this a little bit later as we're moving ahead. So let me see. How am I going to do this here? All right, so all of the writes, this needs to be done with IO write 32, and we got to write something somewhere. So what we're going to do is we're going to take the DMA. What am I doing here? I need to remind myself exactly how this works. Okay, so the DMA memory is our view of the region address of the DMA region that we've allocated. The DMA region address, this is what we use for the hardware. So we're going to use that, and then I'm going to add 0 for this first one. Actually, I should just write this somewhere out here. All right. Yeah, I should just create variables for everything for the time being, and then we'll go ahead and write it. So that's not going to be. I need a DMA address, right? That's what I need here for each one of these here. Okay, so DMA ADDRT RxQ buffer and TXQ buffer and RxCQ buffer and TXCQ buffer. All right, and these are all going to be set equal to the DMA region address plus some offset. So I should just make this bigger. I'll allocate a megabyte so I got plenty of space. All right, so I'll put this first, and then I'll just continue incrementing here. So this will be 1,000, this will be 2,000, this will be 3,000. That's pretty straightforward. Okay, great. And now I can write the addresses for these things, right? So I can set up each one of these in turn. So I'm just going to do this in line for now. This is IO write 32, and this is going to be I want to do. Okay, I need to get the bar, right? I'm writing to the bar. Oh, and I also need to write the correct value. So I'm going to put. And actually, I kind of did this backwards, didn't I? I want to do the enable step last and not first. Let me go ahead and fix that over here. So all of these enables, that should be last. All right, so I'm going to move this up and move this up. All right, great. That's pretty straightforward. Okay, so that's what I actually want to do in the driver. We set everything up, then we enable the queue. Actually, really what we should do is not that, but the conservative thing to do is, hang on a second, let me get this correct. I'm going to duplicate that. Maybe you guys see where I'm going with this. I'm going to do that, and then I'm going to go every other one of these and disable it. So the first thing I'm going to do is I'm going to disable the queue, then I'm going to configure it, and then I'm going to enable it. Simple. Okay. Great. Let me go back to the driver here, and we're going to do that same thing. So for each one of these, I'm going to write to the bar plus 200. Okay. It doesn't actually matter if we write the length or not. And then 204, I'm going to write 0. And then 208, I need to write the address, right? So this is going to be the RX buffer. Actually, I guess what I should do is have both of these. So that's the DMA address, and then void pointer RxQ buffer, and this is going to be based on the DMA region, and then we do the same thing here. All right. So all this is going to get cleaned up a little bit later. That's TXQ. This is RxCQ and TXCQ, and this is 3, 2. All right. So RX DMA buffer and 0xFFFFF. So we take the lower 32 bits, and then we do it one more time for the upper 32 bits. Now, why am I not using an IO write 64? I actually should double check on that to see exactly which module I'm using, but one of the AXI Light Master modules only supports 32-bit operations. The other one supports 32 and 64-bit operations. So I think I'm using the one that only supports 32-bit operations. So if I was to do an IO write 64, it would be discarded. Yeah, which is not what I want. So, all right. So that's the register values that have to be written. And I'm going to do this again for all of these, right? So there's the RX queue, and this will be the RX completion queue, or I guess TX queue, and then the RX. Yeah, anyway, it doesn't really matter too much the order that we're doing these in here. Ultimately, long term, you would want to do these in a more specific order, but we'll cross that bridge when we get there. All right, so here's the RX queue at 200. The TX queue is at 100, right? So that's 100, and this is the TX. All right. And then we do the completion queues. The completion queues don't have this. All right, so this is going to be completion queues, and these are the TX completion queues here. And I think the way I did this is this was 3, and this was 4. Yeah, I kind of did this in a different order here, but this is RxCQ 400, RxCQ 400. Okay, there we go. I think that covers everything. And Vivado is still complaining about something. Okay, so we have mod port mismatch for source versus sync. ARBMux 936. Okay, I think this is a problem in the completion write. Yeah. Why did Verilator not complain about that? Oh boy, I was not expecting to find this many Verilator bugs today. I should be taking notes of all of these bugs so I can report them. Let me double check if everything else is correct here. So this one should be source. Yes, that is source. This one for the RX, right? I have sync for the data, sync for the descriptor, source for the completion. That looks right. And I have sync for the descriptor, source for the data, source for the completion. Okay, I think that's right now, maybe. Oh, put that away. Okay. Going back now to driver. Okay, so I think I have all the queues initialized here. The next step then is to actually make an attempt to send and receive a packet. So I'm going to go ahead and delete all of this. And I don't need to do that. I don't need to do that. All right. So what I'm going to do now is create an RX buffer. And this is again just going to be pulled out of the DMA region. Okay. And this is going to be, I'll put this a little bit higher up. And then we also need a TX buffer as well, right? And I need to get the DMA addresses for these, which is the same thing, right? So this is going to be the RX DMA buffer, same thing. And then the TX DMA buffer here with the different offset. Okay, cool. Great. So for RX, what we now need to do is create the descriptor. And that's going to be written into the RX queue. And then we need to actually enqueue that and then basically do the same thing for TX. All right, great. Let me see here. So to create a descriptor, what I'm going to actually do is create a... Oh wait, what? Did Vivado fail again? All right, I need to see what happened here. Something is still problematic here. I think cannot resolve hierarchical name for data width in Corundum micro core line 398. Oh, same problem. And then I think I have the same problem here as well. Okay, address width line 56. All right, I think this is actually fine. Problem I've noticed is that once Vivado runs into one of these problems, it then generates a whole bunch of spurious complaints. So now that I think I've fixed the original one, we'll see what that does. What are we on, like 11th time the charm now? Maybe it'll work this time around? We'll see. Anyway, one step at a time. Getting back to what I was doing here. I need to create a descriptor, right? So I'm going to go over here and let's go ahead and create a new structure. Where was that reference code I was looking at? Okay, so we're going to create a descriptor, and we're going to create a completion, and the idea is that both of these are going to be 16 bytes in size. So for now, I'm going to do U8. I'm going to do U8 reserved 16. This one I'm going to do U8. Oops. U8 reserved 4, and then I'm going to do U32 len, and let me see here. Oh, there should be LE 32 which one was this here? Right, the address. Oh, this should be, sorry, LE64 address. Okay, so we got 4 plus 4 plus 8, that's 16. Perfect. Yeah, 4 plus 4 is 8 plus another 8, that's 16. Yeah, okay, and then over here, that's 16. Perfect. So with that descriptor, we can then, let me see here. I will take the RX buffer. Well, the right syntax. Oh, no, it isn't. All right, so I'm going to set that equal to the RX buffer. Or no. I want the RX ring here, right? RXQ buffer. And plus 0, because we're looking at the I'll do 0 times 16 and make it clear what I'm doing here, right? I'm looking at the first entry in that buffer, and then we're going to do RX desk address, right? And the address is going to be set to the RX buffer. If I can type, wow, all right. Then RX desk length is going to be set to, I'll set it to 4096 for now, right? So that's the same thing that I had in the Python. All right, and then I'm going to do this again on the TX side, right? So this is all going to be TX now. Okay. Now I also need to set some data, or I need to put some data into the packet that we can check on later. Easiest way to do that. Yeah, so I guess we can do, oh, and this, and memcopy is kind of the reverse of some of these things here. All right, so the destination of this is going to be the TX buffer, right? And the source, I'm going to do, oh, got this here. Oops. All right. I think that works, but we'll see. Pointer to that, and then I need a length. Let's see if this builds for the time being here. Oh, hey, Vivado is finally happy, I think. I hope. There is a critical warning about some unconnected pins. All right, on the PCIe block. All right, but I think that's fine. Just get a glance at how things are looking here, just to see if there's anything particularly weird going on. Not seeing anything now that's, I think, a cause for concern. Got some stuff driven by constants, but that's fine. Those are just the LEDs. We got a few ports being driven by constants, but these ports are not being used, so that's fine, I think. Propagating a bunch of stuff, that's fine. So we have some block RAMs. This makes sense, right? Because these are going to be in the DMA RAMs most likely. Some of these are pretty small, which makes sense. Yeah, the completion write, that's very small. The descriptor read, that's very small. We got the main FIFOs for the TX and RX FIFOs. These are going to be the main packet FIFOs. So you can see how small these are, right? 64 by 256. So they're very wide, but not very deep. In fact, this is almost shallow enough to put in distributed RAM. And over here, we've got output FIFO, status FIFO. Oh, these are coming from the DMA engines, right? So DMA engine, RAM, demux, DMA instance. Yeah. Descriptor read in, right? DMA instance. Yep. Okay. PCIe tag table stuff. Yeah. So these are all of the distributed RAMs used for all these internal components. So that all looks reasonable. Doing technology mapping. Okay. Yeah. So here's the critical warnings here about the unconnected pins on the PCIe block, but that's, I think, fine. There's the error core, error uncore. All right, I'll hook those up at some point, but not that big of a deal. As long as that's not a DRC error later on. Hope that's not a problem, but we'll see. Yeah, now that I have these new wrappers, Vivado likes to complain about not being able to find these modules in the design because they're not actually used. But yeah, this is looking reasonable so far. Yeah. Yeah, it's like once you get the synthesis to go, then the rest of it is seems to come together reasonably nicely. So, all right. We'll see how that works. Okay, what I was going to do, let me find my build thing here. There we go. Let me see if this is happy or if I need to fix some stuff. Oh boy. Oh, I have all of these backwards. Great. Great. Yeah, that's easy to do. So let me go, and it's also easy to fix, fortunately. Okay, do that. Run this again. That should fix a lot of stuff, but maybe not all of it. Okay, what are we unhappy with here? Invalid initializer. Oh, because I forgot to make these pointers, right? There should be a pointer, and this, there should be a pointer as well. Okay, great. And I think I will need to maybe add an explicit cast. Oh, right. And these should be DMA buff, right? Yes. Otherwise, that's not going to work. Okay, let's try that. How does that look? All right, and I may also need to. This is always a good habit to get into. Is making sure that things are potentially endian swapped if necessary. So let me double check how that needs to be done here. I think I need to go over here. Let's see, where was that line I was looking for? Okay, there we go. So CPU to, oops, CPU to LE32. U2 LE64, and same thing here. And similarly, CPU to LE64. All right, great. Okay. Second to build. All right, so this is complaining about a bunch of unused pointers, which, whatever, we're going to ignore that. Okay, so this goes ahead and creates everything, and then the next thing we need to do is we've created the descriptor, and then I need to increment the producer pointer. So I do rxq prod plus plus, right? And I guess I'm going to do the same thing here, txq prod plus plus, and then I need to actually write those. So in this case, I'm going to copy one of these lines here. This is going to be for, well, all right, so this is going to be for the txq. This is the one that I want here. I'm going to make this more clear. This is txq prod, and this is rxq prod. All right, so I will take the rxq prod and we'll put that here, and then again the txq prod over here. That's going to be 104. Okay. Now, what else do we need to do? So we've gone ahead and we've basically triggered all of that. Now I need to wait a little while and then hex dump the buffer. So let me see if I have some code for that I can just pull over. I know the Linux kernel has some nice hex dump macros, but I can never remember what they are. So I gotta see. I think one of these other test modules that I have has those used, so I can just copy and paste them basically. Okay, here we go. I guess there's, all right, so I'll do m sleep 10 and then print hex dump turn info dump prefix none 16.1, and then I want to print the rx buffer. I think that's what I need. Oops. Yeah, it should be txqprod. All right. Then msleep was not defined. I probably need to import something else. Delay, right. Okay. This is just like a quick and dirty sanity check sort of thing, right? So this should print out the contents of our test data afterwards. Let me see what Vivado is up to at the moment. Vivado is, what is it doing? Placement? Looks like placement. Weighted timing summary. Depositing routes. Oh, did this I might need to take a look at something. So intermediate timing summary minus 0.175. This is probably close enough to test. I need to take, oh yeah, it did actually close timing. All right, let me take a look at that timing report and see what happened. What specific path are we having trouble with here? Where would that be? That would be under runs. And this is not showing all of the folders, is it? Great. All right, so I will go up from here, FPGA 10G, FPGA runs, implementation, and we'll go timing summary routed RPT. And we're looking at, oh, that's just summary, intra-clock table. This, oh, interclock table, there we go. All right, so we're looking at the TX out clock. Something does not seem quite right here. So this is, you say user clock to GTY E4 channel TX out clock 3. All right, so, all right. All right. All right, cat cam. One moment. Cat cam, there we go. Perfect. All right, let me see if we can figure out what's going on here. So this seems to be some sort of a CDC path, but what the heck is going on here? This doesn't make any sense. guess I need to take a closer look at where this is showing up further down. I guess the expedient thing to do is probably to open up Vado, but well, let's see what we can find here. Looking at a cross clock domain path. Actually, I wonder if I can just search for that 0.005 number. Yeah, okay, here we go. What the heck are we seeing here? So this is source. This is CIRQ sequence number 1 going to TX done reg. This seems like it's a clock that's coming from an internal, I think, 500 megahertz clock domain related to the PCIe core feeding into the PCI user clock domain. So I think there's some signals that will need to be buffered in user logic first, you know, before they're used, because this really short period is resulting in timing violations, or something very close to a timing violation. Are all of these coming off of the same frappin pin? I think they are, probably, right? This is PCI RQ sequence number 1, PCI RQ sequence number 1. Okay. That's interesting. I'll have to take a look at how I've handled that in the, previously. Oh, cat ran off. All right. Cat cam, we can turn that off. All right. Great. So I think this may actually be in a position where we can test it. Assuming I didn't have a DRC error or something. Yeah, okay, that created a bitmap. We can test it. Very cool. Let me try a make program. I should all be plugged in here. Yeah, we got USB up. We're getting a green light on the JTAG cable. We've gone ahead and triggered the programming process. So what I need to do next is cat showed up, cat ran off. Yeah, unfortunately, he comes and goes. He'll be back. He'll be back. I guarantee it. Okay. That is programming the FPGA. As soon as that's done, then we can go ahead and make an attempt to run it. So I'm going to go ahead and connect to the computer here, assuming I don't fat finger anything. Okay, so there we are. We're looking at the D message on there. Now let me find the other terminal that I had open. Okay, that was the one I had open locally. Alright, so that was on the other end. Okay, great. I need to figure out why this is not accepting my Rapin SSH key. It's rather annoying. I'm going to remove that, and then I think I had another window that I was using for rsync. Okay, there we go. Alright, let me see. Did Vivado finish the programming operation? Oops, not that one. Got so many windows open. Okay, so this one, end of startup status high. That looks good. Now what I need to do is I need to do a hot reset. Oh, actually, what was that device again? This, I think, was showing up as BE. Yeah. So this is whatever these cards show up by default. Whatever's loaded in the flash, that's how it enumerates. Let's see, what was I going to do? scripts. Hot reset, and I'm gonna hot reset that card. Okay, so it looks like that worked. Now let me see. Pseudo. All right, so this has enumerated properly at 8 by 8. Okay, well, let me go ahead and build this. Let's go for broke then, right? Is this going to crash? Or is this actually going to do something useful? It worked. Look at that. Look at that. So this was the output of, what was I looking at here? The RX buffer, right? So that means we were able to send a packet and receive it, and there we are. We got it in the buffer. So this is cause for some celebration here. This is the first packet that the new design has sent and received in hardware. So if I can snap a copy of that. Oink. Very nice, very nice. All right, so I'm going to go ahead and copy this. And just for a second, I'm going to switch angles so I can go ahead and post this on Zulip. Okay, there we go. Very nice. All right, let me switch back to, there we go. Okay, so, let me think. I think there's a couple of other things. Yeah, there's a question, if there's no RX descriptors and a packet comes in, will the design drop it? Yes. Let's take a look at the code and see how that works, right? If we look at the RX path, what does this control logic do, right? The packet. So the first thing that happens is we go out of idle, or we start an idle, and we're going to trigger a request, a transfer request to the internal DMA engine here. So this will take the packet and it will write it out to basically the start of the internal RAM. So these are not relevant, but this one will write it out to the start of the internal RAM, starting at address 0. Then we move over to the RX data state where we wait for that operation to complete. When that operation completes, we'll also have the length of the packet, so we'll store that in a couple different places. We'll put that in the completion, and we'll store it in the descriptor for the PCIe DMA engine, right? So we'll go ahead and store that. Then we'll issue a request for the descriptor, and we'll move over to the redescriptor state. So this one will wait for that descriptor to come in. If the queue is empty, then we get a descriptor with tuser set, and we just go back to idle. So we don't like explicitly drop the packet, but the packet is effectively dropped at this point because then the next packet will overwrite it in the buffer. If we're doing something more complicated and we have some like memory management in that buffer, then we might need to do something, you know, more complex than just go back to idle. So yeah, if the descriptor read fails, then yeah, we just go back to idle. If it succeeds, then we trigger the transfer back to the host, and then move to write data where we wait for that operation to complete. Then we generate the completion and move back to idle. So that is that's that. Right. Okay. Let me think about what else needs to be done here if we're actually going to make this thing work. Okay. So the next thing I'm going to do is I'm going to go ahead and switch to, we need to look at the completion data that comes out of this, because some adjustments need to be made to the completion data before this is going to be useful. So I'm going to add a couple of prints here so we can see exactly what's going on here. So I'm going to be a read RX buffer, and I'm going to do another read here for the TX buffer. So I'm going to read the TX buffer, right? And this is going to be the TX buffer. Okay. And then I'm going to do a couple of other things here. So read the RX buffer, read the TX buffer. I'm also going to read the TX, read TXQ and read RXQ. Well, and also the TX and RX completion queues. Right. Okay. TXCQ buffer. All right. Great. So I'm going to take all of that. I'm going to paste that down here, and we're going to read all of the RXQs as well. So here's RXQ and RXCQ. RXQ buffer, RXCQ. And actually, I'll put the read the RX buffer all the way at the bottom, right? So we have the transmit buffer, we have the transmit queue, transmit completion queue, RXQ, RXCQ, and then the RX buffer. All right. So let's go ahead and copy that across, and we'll rerun this and see what we get. All right, so let me go ahead. That's that, and then I also need this. No, it wasn't that window. Something is getting me tripped up here. That one. All right. Rsync it. Okay, rsync it, then I build it. Insmod it. And rmmod it. Okay. So we can see here, this is the TX buffer, and we have the data sitting in here that we're going to send. Here is the TXQ, so here's the descriptor. TXCQ, well, I don't actually write anything right now in the completion queue, so there's nothing in there. The RXCQ, we can see some information here. So this is going to be, oh, RXQ, never mind. That is the descriptor. RXCQ, we have nothing. Okay, so that is a problem because I think it should have at least written the length in here. So the question is, what did I screw up? I must have screwed up something here. So the RXCQ buffer, that's set here. RXCQ DMA buffer, that is set here, and I do enable that. This is all 400 RXCQ. Would that be? I think I got the addresses right for that, right? Let me double check on that. That would be here where I have that defined, right? So the RXCQ, yeah. So 400, 408, 40C. And let me double check. When I ran the simulation for this thing, when I run the simulation for this, oh, actually, that's a good point. Do I even see that completion come through? So I've got, so we see the interrupt here that gets fired off. I only see one interrupt. There should be another interrupt when it writes the completion for the read operation. Why is there only one? They say the plot thickens, right? Okay, so this is the data being written for RX, but I don't see the completion. Now, it's possible I haven't waited long enough, but take a look at the waveforms and see if we can figure out what happened here. So let me go ahead and clear this out. Take a look and try to figure out what is going on. So with the RX module here, where is that going to be? Yeah, RX instance, that should be correct. All right, so I will add that. And right, so we have the descriptor request going out, right? So we're in state 1, descriptor request goes out as the packet arrives, right? We go to state 2 and then state 3 and then back to idle temporarily. All right, let me take a look then at the completion that should be generated out of here. Okay, so we do get a pulse, but T-ready is just... Okay, so this gets latched in, but then nothing happens. That's interesting. So let me take a look then. We see on the TX side what's going on here. So obviously we got some kind of a bug. I'm just not sure exactly what's going on here. All right, so TX bug, let me see our TX path. Let me take a look at this here. So this one, okay, so we get a pulse here on T-valid, but T-ready is still high. In this case, we get a pulse and then T-ready goes low. All right, let's take a look at the completion write module then. Where is this getting stuck? All right, let me add all these signals. So I've been in state 1, I go to state 2, go back to state 1. We have the IRQ pulse. I don't see anything following this. All right. What do I have going on in here? So CPL combined, let me take a look at that. So combined T-valid, we get a pulse, and then subsequent to that, I get nothing. All right. So let me take a look at the MUX instance. What is going on here? I just got to keep going deeper and deeper and deeper to try and figure out what is, where is this going wrong? So M-access T-valid, but somehow that doesn't get fired off again. So parameters, let's see, there should be 2 ports set up here. S count is set to 2. All right, I guess I need to take a look at that, that MUX instance. Oh, I know what happened. Yeah, I forgot to set the T-last bit, and the MUX is waiting for that, so it got stuck. Okay. Let me see here. Yeah, somehow I just forgot to put T-last here. Okay, so that goes here, and again, that needs to go... Where does that need to go? Over here. Perfect. Okay. Let's try that. We'll go ahead and do a rebuild here. We'll see what that does. Then what else do I need to do? Yeah, I don't know how I missed that signal. That's just a minor oversight. But all right, this should solve that problem, I think. And then we should get a descriptor written back. Now, the last thing I need to do is actually, well, I guess there's maybe 2 other things I need to do. One of them is I need to mask those pointers appropriately, such that they're actually constrained to the defined size of the buffer. So I need to do that. And then I also need to get the phase tag bit working, and the phase tag bit gets pulled from the Q state. All right, so what I need to do is when I do this calculation here, I need to mask off the pointer based on the size. Oh, and I guess one other thing I should just go ahead and do is see if I can register that signal to reduce that timing pressure. Let me just take a look at, see if I can figure out where I've done that in the past. As that was on the, I guess I'll just pull this over here so we can take a quick look at this. This is what I've been looking at in terms of the old Corundum code. And you can see how many signals there are for everything, which doesn't help. Yeah, so this should be the PCI Express logic for this. This goes through the PCI Express interface module here. All right, let me take a look at that. So that is the PCI Express interface module for ultrascale, and I can go ahead and take this, and this goes into the RQ module. All right, so RQ, you can take that, and this one is getting passed straight through to the output. All right, so let me take a look at one of the Corundum designs then. See if I can figure out. Actually, before I do that, I'm going to take a look at maybe just one of the PCI Express example designs here. I think this is a problem for all of these designs. Not registered here. Also not registered here. That's perplexing. Now let me take a look at Corundum then and see if that's set up for one of those. Right, so I'll go to say the Alveo design. Take a look at the core logic for that really quick here. What was I looking for again? Right, the PCI Express. Oh, actually, I guess I don't want the core logic. I want the top level for one of these. Doesn't really matter. There's the PCI Express core itself. All right, so here's the sequence number. Is that just directly connected? Aha, there we go. Yep. So I went ahead and added a register slice for all of these. Yeah. Okay, that makes sense. So I just put that right down below the core to alleviate that timing pressure. All right, so we'll go ahead and add that. Well, should I add it at the top level? I think I'm actually going to add it in this module because I'm always going to need that register to break that timing path. So, all right, actually, I'm going to copy that. All right. Okay, so let's go ahead and create these. This is going to be logic, reg. All of these are 0. All right, so that, and I do always at PCIe clock. All right, this actually should be always FF. All right. As they say, old habits die hard, right? Okay, PCIe reset. Again, going to be resetting the valid signals here. All right. And then all 4 of these get registered up here. Okay. Okay, that looks good. And then I can go ahead and run the registered signals in here. Okay, very nice, very nice. All right, so I'm going to add a note here. Actually, well, I don't know where I want to put this. I guess it's not always necessary. I can, okay, maybe what I will do actually, not right now, but I will add a parameter to turn this registered slice on if necessary. Okay, so that should take care of that. Now I need to go take a look at the logic again for the descriptors and completions here. All right, so what we need to do is mask off these pointers based on that size register. And what is the best way to do that? Let me think here. How did I do it previously? Let me take a look at the old Corundum code really quick just to remember exactly what syntax I used for that, because I'm basically doing exactly the same thing. I need to go back into, where is this? Not any of that. I need to go lib. Oh no, common. And then I need to go to, where is this going to be? This is going to be, yeah, like RX. No. The queue managers. Oh, I guess these are code I've been intending on rewriting. So, okay, they're in a different, they have a different prefix than they're supposed to have. Alright, so in this case, we're going to do a very similar, yeah, so we can see here where that is actually masked off. So, log block size, log queue size, so queue pointer width shift by queue pointer width minus the log queue size. Alright, so that's what I'm going to do. Is this one is going to be ANDed with, what is this one? This is going to be, well, alright, I'll do it this way. That shifted by 16 minus TXCQ size. Right? I think that's right. And then I multiply that by 16. Alright. Something is unhappy about the syntax. I guess because I need to close another parenthesis over here. Okay, great. So I can now copy this and do the same thing here. And this is going to be the RxCQ. RxCQ size, and then I need to do the same thing again for the descriptor read. Alright, so this is the RxQ cons pointer reg. Okay, and then this is the RxQ size. Alright, great. So I take that and one more, I put it down here, and this becomes TXQ and TXQ size. Alright, great. So that should handle the size. Now, the last thing that I need to do, I think, is to get that phase tag bit working in the completion right. Now, this is a little bit less trivial to do because that bit needs to be set for when the actual DMA engine comes in and reads the descriptor. But I don't know what that bit is when the descriptor is being written. Alright. Let me see with the old Corundum code how I did that. As I think I did like a custom DMA engine or something for this to actually work correctly. So this completion queue manager, okay, so yeah, it is going to be the CPL write logic. And when this comes in, let me see here. So we're going to get the completion, it comes in, how does this work? Completion write request input, oh, okay, I see. So this is going to be, right, so here's the completion data. And that's going to be handled there. Desk table start data. Actually, so I guess this module could end up being significantly simplified. Main thing that I need to do is to make sure that I have the logic to read these things out. So I think the trick is what's going on here, right? Because when we read this, we're going to read, yeah, here's the phase tag bit and then the table data here. Okay. That I think makes sense. So let me see realistically with the completion right, what I'm actually going to end up doing here is getting rid of the internal DMA engine. So we'll just have the completion come out. The completion will be presented on the AXI stream bus, and then when the read comes in from the main DMA engine, we'll just return the completion data directly with the appropriate modification. So both of these are, or all these are going to go away. And let me think about this here. So what I need to do now is this DMA descriptor is also going to go away because I don't need that. And this DMA descriptor here goes away as well. All right, and I need the PSDP RAM file here. Let me go ahead. I'm just going to copy. I don't know if I need all of this or not. Yeah, I'll just copy all of it for now, and then if things need to be cleaned up later, I can do that. All right. So this is going to go into the completion right, and I'm going to go ahead and put it down at the bottom here. Yeah, so I do need the mux still, and I'll put this here. Okay. So RAM ADDR width used anywhere? No, so I'll get rid of that parameter. All right, so I extract this DMA RAM write because all right, so we don't actually need any of the write related logic, but we do need to read. So I'll go ahead and replace all this with RD, and we don't need the byte enable. Actually, no, I guess we do. I will leave these alone for now. Hang on a second. Okay, so this one can go away. Okay, this one also can go away because I only have the one. There is no actual memory. Write done. We're not handling writes, so that goes away. I do have the read response. I don't know if I need the pipeline necessarily, but we'll leave it alone for now. Go ahead and have that. This is for writes. That goes away. That goes away as well. All right, so this is what we need for reads. And the part that we need to mess with is this one. Okay, great. So all I need to do now is put in the descriptor here. And I think that's everything, right? So there's a couple more things I need to do, but we'll take the descriptor. This will be from the combined interface here, CPL combined. And I will put data here. Okay, I think that makes sense. And then the other thing that I need is the phase tag bit as well. So I need another register for that. I'll create another register over here for the phase tag bit. Logic phase tag reg. Okay. And then the phase tag bit that will be set over here somewhere. All right. So let me think about this here. So we're waiting for this to show up, and what is it that we need to do? So the idle, this state goes away basically because I don't need I don't have this internal descriptor anymore. That goes away. So source address, reading from address 0, that makes sense. All right, so this is going to be coming from, no. All right, so the phase tag reg, I need that in a minute. What I am doing now is I'm looking at the combined completion. I need to move this so I can actually access that. Put this up here. All right, so I'm going to take the combined completion. I need, looking at TID on that, right? And then again, I'm looking at, oops, okay, that's correct. All right, okay, so now I'm looking at this one, .tvalid. Okay, if it is valid, then I can continue. And what I can do as well, okay, is I can set the phase tag bit, and this is going to be set to, right, the producer pointer reg. And what is this going to be? I want to say it's, is it just the, txcq size plus 1, and then I invert that. I think that's right. So if a txcq size was 8, that's 256 entries. So I want to take the, bit 8, the 9th bit. Okay, I invert that. That gets me the tag. Okay, perfect. And then I do the same thing over here, and this becomes the rxcq and rxcq size. That gets me the phase tag bit. Okay, great. That's looking excellent at this point. Okay, and the other thing I need to do now is I need to set the t ready of this to 0. Okay, and when we fire off the write data, once this is done, then I need to accept the descriptor. Oops, 1 prime b1. Okay, there we go. There we go. So the start side is 0. I set that to 1 to accept it. Then I move on to the next one. Okay, perfect. I just need to make sure I'm also not accidentally clocking in an extra one here. Okay, great. So valid and not ready, then I can proceed with doing this. So I set the phase tag bit. Okay, great. Okay, now I need to transfer the phase tag bit. So what I'm going to do actually is I'm going to have the phase tag reg here, 126 down to 0. So I'm going to set just the last bit of the, oops, if I can not make any typos, that would be helpful. Okay, I'll leave that there. That's I think just fine. Okay, so right, I'm setting the highest order bit of the completion equal to that. All right, so let me go ahead and run the test again here, and we'll see how badly this blows up. I think maybe all the pieces are in place. Oh, all right, so we have some complaints here. Okay, so pipeline and size. I think int address width. What is this? Size over segs times seg de width. I don't know. I'll just make this like, it doesn't really matter. We're only hitting the first entry anyway, so. Oh, and then pipeline. Yeah, all right. So pipeline, I'm just going to set this to 1 because we don't really care too much about the pipeline here. And then 1 minus 1, that will become 0. Right, okay. And I can probably clean that up more later, but whatever. This will be a starting point here. Oh, size is not defined. All right, this is just whatever. All right, I can get rid of that. Now it's probably going to complain about some width problems that I'll have to fix. What did I say? Lots of width problems. Okay. It expects 64 bits, but it generates 16 bits. Oh, is that the case for all of these? Not all of them. Okay. Expects 256, but it generates, well, that's fine. Do that for now. That'll need to be fixed later, but whatever. Alright, and then I have a bunch of these here that are complaining about the width. Alright, so let me see here. I have 2 instances here, so I gotta do, alright, these are just fixed 64 bits for now. So I'll just do that, and 64 again here. Okay, and for descriptor read, same kind of thing here. Okay. Have we finally satisfied? Nope. Okay, something else is unhappy here. Shift R expects 64 bits on the left-hand side, but the replicate generates 16 bits. Why would it expect 64 bits? No, okay. All right, well, I'm just gonna try adding that, and we'll see if that makes Verilator happy. Yeah, it's like, I don't know where it's getting this 64 bits from. That should be just triggering a cast to 64, but not actually requiring 64 bits. Yeah, an operator AND expects 64 bits, but the shifter generates 16 bits. Why would this be expecting so many bits? Oh, wait a second. This is definitely something I need to fix here. That needs to be properly nested. Otherwise we have an issue. Because I just want to shift that portion of it, not the whole thing. Or wait a second. Okay. Let me just make sure I have all this nested correctly. So that is the shift amount. This one is... Okay, no, that should be fine. I shouldn't need to add an additional set of parentheses there. Right, so I already had that. I just put that 16 prime in front of it. Okay. We do that, then we multiply by 16. Alright, fine. Let me just force this to 16 bits. Is that going to be what we need? Actually remove that and remove that. I'll put the 16 here. Okay, let's try that. Okay, there we go. Verilator was happy with that, so let's let that go, and at the same time I'm going to kick off another Vivado build. And let's see here, I'll do make, and we'll see what that does. Alright. So we'll let that run, and we'll see what that does. Once this simulation is complete, then we'll take a look at what the what our little test driver does and whether it's printing out things correctly. And then, well, okay, we'll make sure the test bench is doing the right thing, and then we'll repeat the same test on the host. Assuming it works, which I think there's a pretty good chance that it will, the next step then is to actually start building the actual network device driver. And this is where things start to get a little bit more complicated, because there's when you start interfacing with the host network stack, then you need to add a lot more APIs. So let me take a look at the Corundum device driver to remind myself of exactly what needs to be done here, and then we can start implementing the same thing. So let's see, for the Corundum device driver, I've got a bunch of files. I might as well just look at this at the same time here. I've got a bunch of files for like the completion queue, for the event queue, for RX and TX, but I guess I don't have separate files for receive and transmit. What was the common file for that? Like, was it ring? Res? Oh, well, I guess, yeah, alright. So RX and TX are set up to handle that. So this one is create RX ring, destroy RX ring, open RX ring, close RX ring, and I think the transmit and receive code are in here as well. Yeah, so this one handles you know, processing the RX completion queues, and for TX we're handling you know, the same kind of thing. Well, in this case we're not processing the completion queues. In this case we have where is it? Start transmit. Okay, that's the entry point that we're interested in here. So there's a bit of infrastructure that needs to be set up for all this to work. So let me see. We don't need all this code because there's a lot of ancillary features and whatnot. So stripping it to its core, it's there's quite a bit of stuff that can potentially be removed. So let me see here. Yeah, so what we need to implement effectively is this create netdev call first, and this one has this structure associated with it called net device ops. So this defines all of the entry points that are associated with the network device. So we've got open and close for basically starting and stopping the port, and then start xmit is how you actually transmit a packet. The rest of these are somewhat ancillary, right? So get statistics, validate address, set MAC address, change MTU, Ethernet, IOCTL, and get devlink port. So all of these things are, like I said, somewhat ancillary. So we can forget about everything except like the first three and just implement those, which wouldn't be terrible. Yeah, but I probably need to create some of the other logic for this to work. I actually don't think this is going to be too bad, because if I don't encapsulate things too much from the get-go, I'm not going to have to create too much additional boilerplate for all this to work. I'm just going to have to create what do I need, right? I need to create like the four memory regions. Yeah, 4 memory regions for the transmit and receive queues, and I can just do that statically. Obviously long term that's not the optimal way of going, but we'll start with something simple and then iterate from there. Yeah, okay, so the create net device creates the thing, the destroy net device tears it down, and I don't think this is going to be all that big of a deal to make it work. Let me see here. I'm just refreshing my memory on how this works. So we allocate it, right, and we provide the resource counts. We need to set the device. I think we can skip that. Set the private data, or init private data. Let's see. Okay, so this is just zeroing the private data. This allocates it, I think. Yeah, okay, size of priv. Okay, then we get the private data block, and then we can use that. So spin lock init for stats lock, we can ignore that. This sets a bunch of stuff in the private data structure, and that one I think is defined over here, right? We have the private data structure. Where is that? There's a lot of data structures for all this stuff. I think it's probably down near the bottom. That, yeah, okay, here we go. So obviously there's a lot in here, but you don't need all this just for the most basic functionality. Oh, this simulation ran, and we can see 1 MSI interrupt, 2 MSI interrupts. Now, what else do we need to look at here? Okay, RxRQ frame. Yeah, so here is 1 completion. This is for the transmit completion. And we can see 1, 2, 3, 4, 5. No, I guess it would just be 1, 2, 3, 4. So that's the data, and we can see the phase tag bit set. And for this one, for the receive, 1, 2, 3, 4. Oh. Why did that happen? There should be a length in here, I think. Unless did I forget to set that somehow? Alright, I need to take a look at the waveforms again and try to figure out what happened. Alright, so refresh. Okay, that looks better. Because now this is actually going back to idle. Now what I need to figure out is why the receive path didn't set the length, or why that's not getting passed all the way through. Alright, 4-inch completion right. Yeah, all right. So I need to take a look at the well, this should be completion 1, right? Okay, yeah, so the data value in here is bogus. All right, I need to fix that. One moment, where is that? Looking at the wrong window. Okay. This one, okay. This is going to be it's not the completion right that's messing up, it's actually the RX that's messing up here. All right, so the completion data. Why does that continue getting updated after that point? Oh. Duh. If I set it to 0, it's going to be 0, right? Hey, alright, let me see. TX, that's also set to 0 here. Great. Not 0. Not what I want. Okay. Okay, well, great. Yeah, so in this case, I'm not really reporting anything additional in the completion records. Ultimately, in the long term, the completion records would contain additional information like timestamps, for example. Or for receive packets, you might include checksum information. So if you do checksum offloading, then you would put the checksum in the completion. For TX and RX, you would include PTP timestamps in the completion records, that sort of thing. I mean, not all NICs actually do that. There's a lot of NICs that you have to read the PTP timestamp out of registers, but that's, the whole point of Corundum is to support timesync, first class. You're going to timestamp everything, provide timestamps for everything, so that, we have to put the timestamp in all the completion records. Right. Another thing, I guess, is you don't necessarily have to provide a completion for every single packet being sent. I know this is something, at least for, RDMA, where you can enable whether or not you want a completion, and or for a given request, and because everything gets processed in order, then when you get a completion for a particular operation, or everything gets processed in order on a given queue. So when you get a completion, actually, let me make sure that I've restarted Bavato here. I don't think I did. All right. We got to make sure we're actually building a design that's going to work. Before I get too much further along here. Okay, great. So fire off make on that. Anyway, what I was saying in terms of RDMA is that within a queue, all of the operations get processed in sequence. So if you want to queue up like 5 operations, you can just mark the last one to generate a completion, and the ones preceding it won't generate completions, and you just need to wait for that one completion. I don't necessarily know if it makes sense to do that for like Ethernet traffic generally, but it is a feature that probably should be implemented. I'm not going to implement that now. Again, this data path is just supposed to be sort of the most basic possible data path. And then, building on top of this will be some of the more complex features. Well, I guess not even really building on top of this. I think what I mentioned before is kind of the overall plan, right? We're going to build this really simple, straightforward data path, and then we're going to ship a Theseus it into something useful. So that means that basically the whole thing is going to be rewritten piece by piece. All right, here we go. Now we have something useful, right? So here is the data that got written, right? We got 1, 2, 3, 4 D words. The last one has the phase tag bit set, and this one has our length 3C. And I think that's right, because 40 would be 64 bytes, so 3C is 4 less than that. So that's a 60 byte minimum length frame. And that makes sense, yeah. That also makes sense here. If we look at this, this is 15 D words, FF, so 15 times 4 is 15, 30, 60, right? So 60 bytes. So the math is mathin'. That's always a good thing. Yeah. So this finally looks correct. At this point, I just need to validate that this does the same thing in the actual hardware, and then hopefully we can get ping working. it's going to take a little while, I think, to get all of the kinks worked out of the network device driver to get an initial version of this working. But this is looking very, very good so far. Oh, I guess one other thing I need to do is actually implement interrupts, because I have not done that yet. Okay, well, we're going to have to wait until this thing finishes building, and then we can kick that off next. Yeah, because the design on there, I think, is borked, right? It's not going to be able to generate any interrupts. Maybe we could reset it. All right, well, we'll just wait for Bravado. It'll take a couple minutes to implement the interrupt handler anyway. Let me take a look at the other reference code I was looking at here. And where is that? Okay, so let me get the interrupt actually set up properly so we can make sure that's working right. That'll be kind of the last thing I think to check. All right, where was the ISR here? Oh, there we go. Okay, let me pull up the kernel module again. Go up to main, and then I'm going to generate an ISR here. So it's going to be static IRQ return P. So the interrupt handler int IRQ and void data. So the cool thing about Linux is they tend to provide lots of places for passing data around. So I can do cdev equals data, and then okay, so cdev IRQ count. So I can increment that. Then I can do dev info. Dev. I can print that out saying we got an interrupt, and then we can return handled. Okay, very cool. That is step number one. The next step is that I actually need to register the interrupt here. So I need to allocate the interrupt vectors, right? And then I need to actually set up the interrupt. So I do ret PCI request, request IRQ, and in this case I do pdev. I think it's IRQ vector 0. So I do the interrupt. Whoops. This is just the function, and then I do 0, and then here's my private structure that gets passed to it. Okay, very cool. So with this, because I'm passing the structure to it, I get it back when the interrupt is fired, which makes everything very nice and easy. Okay, and then I need to do one more thing. If this fails, oh, this was the same thing, was it? All right. I'll have to double check on that. Oh, all right, there we go. So failed to request IRQ. Okay, great. Let me just double check to make sure this is all looking correct. Okay, there we go. Fail IRQ. Okay, and then this one is PCI free IRQ pdev 0. Okay, great. I think that's right. And I need to do this as well after the DMA free coherent. There. Okay. I'm not 100% sure all that's correct, but it's a start anyway. Okay, so we allocate the IRQs, we request the IRQ. At this point, we should be able to fire off the IRQ. All right. Let me see what Vivato's up to. Vivato is still running, so that's going to be a few minutes. I'm going to go ahead and we will try and see if this interrupt gets fired off correctly. Okay, great. So do a make. All right. Now I'm going to do two things. So it has been removed, so I'm going to reset it because I think in its current state it's not actually going to be able to fire off the interrupt. It needs to be reset to clear some stuff out. Then I will do insmod and then rmmod, and let's see. Oh, we have interrupt getting fired off here and interrupt getting fired off here. Well, hey, there you go. So that worked perfectly. So the interrupt gets fired off. Yeah, and the interrupt got fired off once because it gets stuck. And I need to fix that. Okay, well, great. I'm also going to reduce the size of these prints really quick here because this is taking up a lot of real estate. Maybe instead of printing out 256, I'll just, well, for the Qs, I'll just do 32, and this one I'll do, how about 128? Why not? All right, let's try that. And this time, if I do the reload, then it shouldn't fire off the interrupt at all. Because it's, you know, that the receive path is stuck, or the completion write path is stuck. Yeah, so we probed it, we didn't see an interrupt here. For whatever reason, the interrupt always seems to get fired during remove. I don't know why, but there you go. Anyway, this looks to be pretty reasonable. Obviously, the completion queues don't have anything useful in them, so that will be the next step as soon as Vivato's done. It's currently running, doing now. It's doing placement timing optimization. Great. Should only be a couple more minutes before that's done. Okay, so the next thing to do is to start putting together the network device driver. And this is, I mean, all this stuff I'm going to have to go kind of reorganize later once this stuff is put together. Yeah, so this is, again, talking about how you have to register things with the operating system. At some point, this needs to get registered. Let me see here. Definitely port types. Here we go. So yeah, so at the bottom, this registers the net device with the operating system. And when you remove it, it unregisters the net device. You know, pretty straightforward setup here. And when you register the net device, that's when the kernel can potentially start calling these entry points. So you want to make sure everything is set up to handle an open or a close or a start transmit or whatever by the time you call that register call down at the bottom here, wherever this is. Yeah, there we go. Yeah, and then so on the transmit path, when the kernel wants to send a packet, it calls the start xmit function. And if we go take a look at the transmit code here, we can see, if I go down near the bottom, the start transmit call here, it accepts both the net device structure as well as an SK buff, which contains the actual packet data. Now, I'm not going to go too much into the SK buffs for today. Needless to say that the code here is doing some relatively non-trivial things with the content of that SKB. In particular, you can see a bunch of stuff dealing with timestamps and linearizing the SKB, mapping the SKB. Well, we are going to have to map it, but okay, that's we're going to keep things as simple as possible there. Right, so I guess the mapping of the SKB is maybe where things get a little bit interesting as well. So in this case, for those of you not aware, SKB structures are trying to remember how exactly they allocate it. I think what happens is Linux will allocate a block of memory, and it'll put the SKB structure itself at the bottom of that block. And then the top portion of the block will actually contain the packet data. And the SKB will have some pointers into that packet data for the the start and end of the packet and a few other things. I haven't really done too much detailed stuff with SKBs to know exactly what all those pointers are for and whatnot, but in general, the SKBs can come in a couple of different forms. One of them is when you have a linear packet and the entire packet sits inside of that memory region with the SKB data structure at the bottom. But they don't always come that way. So that's why we have a bunch of additional code here, because if the hardware supports scatter-gather DMA, then it's quite common to get an SKB that is fragmented, in which case you have a portion of linear data. Let me see here. DMA map single, I'm trying to remember. Oh, SKB frag DMA map. Yeah, okay, that's right. So yeah, the way this is set up here is that it maps all of the fragments first, then it maps the actual SKB. So this DMA map single is part of getting access to whatever is in the linear portion of the SKB, which is, you know, the memory page or whatever that contains the SKB data structure itself. The fragments are basically memory pages that have been attached to the SKB. And these can exist, you know, scattered throughout memory, and those have to be separately mapped, such that you can actually point the card's DMA engine at the setup. And the reason you run into this particular configuration has to do with basically how the rest of the network stack works. When you want to send, for example, a large block of data over PCI Express, or not a PCI Express, a large block of data over like a TCP socket connection, what will happen is you'll maybe take your, I don't know, 1 megabyte block or something, maybe not a megabyte, maybe like, you know, 100 kilobytes or something. You'll call send on that with the socket. And then what the kernel does at that point is it actually treats that buffer as one absolutely massive packet. And it creates an SKB to deal with the headers. So it'll build the headers up in there, and it basically attaches your buffer to that SKB. If the card supports scatter-gather DMA and it supports like TCP segment offloading, then you'll get a linear portion for the header and a massive block, which could be a bunch of fragments for the, you know, the payload data that needs to be sent. And then it's up to the card to fragment the packet appropriately and replicate the headers and adjust like sequence numbers and checksums and such for all the individual packets, at which point all that gets sent. If the hardware doesn't support TSO, then there's a software implementation. It actually might be like software GSO. I can't remember exactly what the term is for it, but if the card supports scatter gather but not TSO, then what'll happen is that right before handoff to the driver, that software GSO routine will be run, and it will create additional SKBs for all of the individual packets that need to be sent out of that buffer. And the proper, or the memory pages that correspond to the payloads for all of those will be attached to each of the SKBs. So instead of getting one SKB with a massive buffer, you'll get, you know, 5 or 10 SKBs or whatever with a smaller piece of that original buffer. But the point is that when this process happens, the packet data stays put, right? It's a zero copy operation. So all of these packets are all pointing at the original buffer in memory. Actually, I guess maybe that gets copied into kernel space or something during the send call initially, but it doesn't get copied again when these packets are generated, assuming the card supports scatter-gather DMA. If it doesn't support scatter-gather DMA, then all the SKBs have to be linearized. So, and how does the kernel know what is supported and what isn't? Well, if we go back to the net device block here, we can see that there is interface features that get reported here. Wait, where did this come from again? Oh, this actually comes from a higher level point. Is this from interface here? Where is this coming from? Somewhere this information gets built up. I'm trying to remember where that happens. Net devices, creating net devices, port count. IF features. Okay, so that's read from a register. At some point that needs to get mapped into the actual net device features. Well, maybe that's happening over here. Yeah, so when it creates the net device, then it has to look at the features. Okay, all right. So hardware. Okay, here we go. Here we go. Yeah. This is where that happens. So hardware features. At least Corundum by default sets scatter gather, and then it will look for, you know, like checksum. It'll set that. TX checksum. It'll set that, etc., etc. It sets high DMA. You know. I guess this is a placeholder if I need to add more stuff. Yeah, because this is. I was looking at other drivers as I was putting this together. So I think certain bits have to go in certain areas. So there's hardware features, there's netdev hardware features, and there's netdev features. And I'm not 100% sure how those need to be handled. And that ndev is actually coming from, yeah, that's the actual net device structure. So this is not something that I built. That is, that's part of the Linux kernel. Yeah, so in this case, if you support TSO or DSO or whatever, then you would set additional flags here. If you don't set anything, then the kernel will linearize everything. The performance, it'll work, but the performance will be terrible. If you set the scatter gather flag, then it will do the software GSO, and you'll get basically fragmented packets where you'll have the a linearized portion with the header with some pages attached to it. If you set like the TSO or GSO flags as well, then you'll get massive packets, and the hardware will have to jump through some hoops and slice and dice that into the individual pieces. So plan is to support that in the long term, but we'll see exactly what that's going to require. All right, getting back to this here, Bavado was able to successfully build that. Let me actually take a look at what the timing performance looks like. Where are we going here? Okay. So it still had some trouble. 0.097, but it did close here. So, okay. What would be really nice is to get a timing report at this point, right? What paths are these that it's having some trouble with? I don't know. I guess I can take a look. I still have the timing report open, right? Yeah, there we go. Timing summary routed. This should be, I think, the current thing. Yep, okay. And WNS 0.009, that looks pretty good. And the interclock, yeah, we still have something at 0.009. All right, fine. What is that then? All right, let me just select that whole number. Where is that coming from? Okay, so this is now. Oh, this is RCT data 33. Okay. Well, I guess that kind of makes sense if it's just feeding all of the outputs directly. I don't know why. You know, the device is set up to work this way. I thought that it would have some sort of downstream logic to do this clock domain crossing. It seems to be what's happening is that the core itself is set up to run at 500 megahertz, but then the user logic is running at 250. So this core clock here is coming from one of the transceivers. This is a 500 megahertz clock. And then we have another clock, or the PCIe user clock, that's running at 250 megahertz, coming from a different path. Let's see where that's coming from, right? This one is coming from TX out clock to buff GT core clock, which feeds the PCIe EIP core. This one is coming from ETTX out clock to buff GT user clock, which is probably doing a divide by 2, which then provides the user clock here. So, it's a little bit perplexing why they did it that way. Well, it was able to close timing, and this one is actually going through quite a bit of internal logic, so it would make sense why it's having some trouble with that. Because running at 500 megahertz is not such an easy thing to do. Alright, well, figuring that out properly is a problem for a different day, so I'll set that aside. It did close timing. Now we need to load it onto the card and do a quick test. Yeah, somebody's asking, is this PCIe driver and firmware? Yes, it is, and yes, it is eventually going to go in there. I guess I need to do a little bit more cleanup work, but I might as well just put this in as it is. The idea is that this is going to be a precursor to the next generation version of Corundum. So I'm putting together kind of, a rough data path, a very straightforward implementation. Not optimized for high performance or anything, just something to make it work. And then the idea is that once I have that sorted out, the next step will be to build on top of that. And improve the performance and or improve the area. Well, I guess the idea is I'm basically going to make two different designs. One that's optimized for performance at like 100 gigabits per second. The other that's optimized for area. Yeah, it's optimized for area, and then ideally that one will run up to about 25 gigabits per second. But there will be some restrictions on that, and it won't support, all of the features and whatnot. But both versions, the idea is that they will use the exact same device driver. So yeah, there's a bunch of stuff I'm planning on changing that I haven't actually done yet. So one of them is like variable length descriptors. I haven't implemented that yet, but that's one of the things I need to do. I also want to basically scuttle the whole register space and have a queue-based mechanism for configuration. Well, I guess I won't scuttle the whole registers, but you still need registers to configure stuff. But most of the high-level operations will be done via queues. So yeah, once I get the core logic working and, a first version of the new driver working, then it's going to be, iterating until we get all of the details hammered out here. All right, so let me go ahead. I've gone ahead and reloaded it. I'm going to rebuild the FPGA, or not rebuild, reset the FPGA. And then I will insmod that. Okay, so we can see here, we got 2 interrupts fired off, so that's perfect. And for the CQs, okay, for the TX CQ, it's all zeros, which is interesting. But for the RX CQ, we are seeing 80 here, indicating that last bit got set. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, so 16 per row. So that would be one completion, and we are seeing that bit set. But we're not seeing it on the TX side, which is interesting. So why is that? Yeah, you got to make sure your sanity check stuff works before you can get too much further along. All right, so TXQ buffer, TXCQ buffer. All right, so the TXCQ. All right, so TXCQ DMA buffer did get set here. 300, 308, 30C, 300. So it's kind of working. There's still one more thing that isn't working, I guess. So if I can track that down, then we can move on to the next step here. So the question is this an HDL problem, or is this a C code problem in the driver? If we look at the writes that were actually performed in the test bench, although I should rerun this, let me see. If I rerun that, is this going to rebuild or just rerun? I can't remember what I've edited. Okay, I guess it's just rerunning it. Okay, cool. So that should be quick. Okay, so we have, yeah, MSI interrupt, MSI interrupt. We got two MSIs. That's as expected. So here is the completion that got written out, right? We got 3C and 8, and here is the descriptor that got written out, which also looks correct, right? So this is set 3000, that's 1000, so that should be correct. So RxRQ frame 3000. Where was that? Yeah, 308, 3000. So that, I mean, looks correct. Everything can go quite swimmingly until you've made some little mistake somewhere, and then it can be quite difficult to track down. 300, 308, 30C. Okay, so it definitely looks like we're hitting the correct addresses here. This is for the transmit completion queue. Let me double check to make sure I have all the offsets correct in C code, because there is some replication here that makes things somewhat difficult to debug. So TXCQ, that's 3000, that's 2000, that's, well, I put that like 10,000, 20,000 or something. Okay. Right, that's 0, that's 1, that's 2, that's 3. All right, so all of that matches. DMA region address, all that looks fine. Oh, the other possibility is that maybe I need to run some sort of a DMA sync call here. Let me see if there's something obvious from like the transmit or receive code. Where would this be? Like the event queue handles stuff, CQ. All right, so CQ handles some stuff here, right? So if I'm talking about the, oh, that's actually going to be handled locally, I think, in the RX and TX. So if I look at RX, for example, when we are processing the CQ, poll RX CQ, process RX CQ, where is the process RX CQ? EMA RMB. All right, I will try that. Oops. Okay, there we go. Okay, there we go. That worked that time. So here's your TXCQ. Yeah, all right. So it's important to get that kind of stuff figured out, because if something is not, you know, properly cached or whatever, then you can run into weird problems like this. Yeah, okay. So now we are seeing the actual completion record here, and for the read direction we have. Is that length correct? Okay, so something didn't work correctly because this length is not reporting what I was expecting. Previously, did it have the correct value? No. Previously, it was also wrong. Okay. Why are we getting the wrong RxCQ value now? let's see, simulation, did I get the correct result here? Yeah, I got 3C here. So, shoot, why am I getting the wrong length? Looking so promising, right? But then, okay, the length is wrong. All right, so why did that happen? This is annoying because if this is a simulation implementation mismatch, that could be a significant issue. Well, actually, nope, it's not the same as the TXCQ. So this definitely seems to be. Let me think about what is going to be taking place here. Is it possible that that value got changed? So if the, let me think about this for a second here. So if the RX has already moved on to the next packet, for example, why would that propagate through? Because we have the mux in there, which is merging the two together, and that's going to be registering it. So until it gets latched out, it should still have the same value. So let's see, completion right. This, yeah, so ready here. Yeah, so it's set to 0 here at the top. It's set to 1 here only when we get the status back from the DMA engine indicating that the transfer has completed. And that only happens, you know, when it's actually read it. This one is again pulling from the combined CPL bus here, the combined completion bus that pulls the T data. So that looks fine. Well, I guess the question is, which module is messing up? Is this messing up, or is the problem on the other end? I guess it's also possible that Vivado has done something weird in terms of how code is implemented in the RX logic here. It's also possible that that this code is doing the wrong thing for some reason, right? Because if this one sets the length to whatever is in the original descriptor here for a receive, yeah, okay, so I can run an experiment here to see what is going on. So let me set the receive descriptor size to something oddball. How about I set this to 4095 just for kicks, and we'll see what happens there. Right, oh, that's a TX. Oh. Well, that's my mistake. I sent a an MTU size frame. Oops. All right. Yeah, that would do it, wouldn't it? So it's actually, everything is working perfectly. It was a C code problem. All right. Let me see if making that change does anything helpful. Okay, so I will go ahead and rebuild it. Okay, this now reports 3.8. 3.8. And as we say, the plot thickens, right? Because we didn't get 3.8 here, we got 3C, right? Yeah, we got 3C, so somehow we're getting a 4-byte difference. What could be going on there? Oh. Okay, I think maybe I know what's going on. That there is a... Like, what part is actually going to be padding this to the correct length? Well, this seems to be a minor difference in padding. I will investigate what's going on there later. I don't know why we're getting a different value here, but that's maybe not a super high priority. Everything else seems to be looking good. It's just the length is off by 4 bytes. So I don't know if that's a problem that occurred on the RX side and somehow those 4 bytes got lost. Actually, let me just rerun it one more time here and see if we're getting the same value consistently here. Yeah, it seems to be. Let me actually just do a reset of the device, and I will insmod and rmmod, and yeah, so I mean, it looks like it should be correct, but all right, I think this is probably close enough to proceed with building a network device driver for this and see if it works, right? Because we are getting a completion record, we are getting a we are getting a completion record for transmit and a completion record for receive, and the length is, I think it's correct. I suspect there's a difference in the padding somewhere. I don't know exactly what's going on. Yeah, I got to investigate that. But we do have the message here. Actually, I guess a simple thing that I can do. Is that going to make much difference? Yeah, I mean, I could fill the buffer with junk and see what happens, but I think what I should do is just make an attempt to get ping working through this thing. Starting to get a bit low on time here. It's already a pretty long stream at this point, but core datapath at this point seems to be doing what it's supposed to do, and we have this very simple test driver, which is just sending a single test packet through the link. So the next step then is to extend this driver to actually set up the data structures and such appropriately to actually be able to register and use a network device. So let me take a look at what needs to be done for that. Let me see here. Yeah, we'll see how long this is going to take. There's potentially quite a bit of code that needs to be put together for this to work. So we'll see what I can accomplish today. Maybe we won't be able to get all the way through it. Anyway, I'm going to go ahead and start creating some files here. So we'll start with one for the net device. Well, let's see. I'm going to do include, oops. And struct net device. And that's fine. We'll do that for now. And I need to fix the code formatting. This is another annoyance with Z, as I don't know how to do like per folder or per file settings. It seems to be just like per file type. Tyler padded the array. Well, no, because the data, so I got a comment about the length here, saying maybe the compiler padded the array. Well, the data that I'm sending is 15 bytes long. So that should get padded by the transmit MAC, and then the receive MAC, should pass it through without modifying the padding. So somewhere along the line, 4 bytes have gotten lost, and I don't know if that has taken place on the transmit path or on the receive path or what. I'm suspecting right now that maybe there's the transmit MAC didn't pad the data correctly. So it padded it 4 bytes short, but I don't really have any good reasoning for why that would be the case. But it's close to the correct value, so, I guess I can take a quick peek at the files here and just see about the configuration of everything and see if there's something that looks weird. Yeah, so the min frame length is set to 64, so it should be getting padded to 64 bytes, and this is not a parameter that's overridden here, right? So it's just directly passed in, so it should be set the same between both the simulation and the Vivado build. So I mean, if this was getting passed in from somewhere, then maybe there's a difference at the config.tcl level or something, but they're both set to 64. So it should pad it to 64. Then when you strip the 4 bytes off the end, you should get, 60, which is hex 3C, right? And that's what we were getting from the test bench here, right? If we look at this, we get, where was that? Yeah, we get 3C. So that makes sense. But for some reason, this is reporting 3.8. So somewhere along the line, either the frame didn't get padded to the correct length for some reason, or some data bytes were lost in the receive direction, or the length was reported incorrectly. I'm not sure which one of those is actually what happened. And yeah, this is definitely seems to be a simulation implementation mismatch of some sort, because I'm not sure how we would get this difference from software, right? This value has not been touched by software. Yeah, because this is coming directly from the hardware. I guess I'm trying to think if there's any other experiments that I might be able to do to try and figure out what might be going on here. So for the receive queue, actually, hang on a second. So for the TXQ, all right. So the TXQ, I guess it did actually send a slightly different length frame in the first place. That shouldn't be an issue, I don't think. Let me take a look at the, where is this? Okay, here are the TX and RX queues here. In the simulation, it's sent a 15-byte frame. In C, it's sent a 16-byte frame. Actually, I guess because it included the 0 padding at the end. I guess what I can do is I can try one more change here. I can just subtract 1 from the length, and we'll see if that makes any difference. Where did I... Okay, so I'll subtract 1 from the length here, so we're literally sending the exact same thing. Okay, let me rsync that. And then I will pull up, there's that, and there's that. All right, so I will go ahead and make it. Yeah, and that reported 38 as well. So yeah, this is now exactly the same, right? But this one is still reporting 38. So yeah, that's a bit of a head scratcher. But yeah, I'm thinking what I might do is kick the can for now on that, and I'll see if I can get to the bottom of what's going on with that later. Point is, it seems to be working well enough to where I should be able to get the network device driver to do something useful. Because if we can ping, that would be great. But yeah, it's going to take a few minutes to get to that point. So, all right. So let me go back to this here. We're going to create the netdev, and I need to create another structure over here. And this is going to be the netdev priv. Okay, and then I'm going to have to put some stuff in here. Okay. 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 And then I think the rest of this, is there anything else I need to put in here? I have features, link status, queue counts, ring sizes. I guess what I should probably do is move all of this kind of stuff in here for the time being. Well, not so much move it, but at least have references to this stuff. Oh, well, I can access that. I can access that indirectly. But what I should do is deal with the different regions here. So let's see. So this is going to be TXQ, we need TXQ, whoops, TXQ, RXQ, TXQ, RXQ, TXCQ, and RXCQ. Okay, great. So that's all that. Leave that there for now. Actually, I'll just comment that out. Well, yeah, I'll leave that there for now. Okay, so when I create the net device, what do I need to do here? I need to do struct device dev equals cdev dev. All right, and then I also need to do net device. I need that. I need struct. Oh, the private data and int ret 0 and go from there. All right, so ndev equals alloc ether dev mqs size of the private data. Okay, and then we're gonna have one TXQ, one RXQ. I'll definitely expand on that later here. So if not ndev, then this is gonna be dev error dev failed to allocate net device. Okay, and this is return. Okay, so that, and then I do set net dev and dev. So I need to assign that with a device, and let's see, priv equals net dev priv net dev. So the idea is that this goes and allocates the private data. So now I just need to pull out the allocation that it made, and I'm going to go ahead and zero it. Okay, so we'll go ahead and zero it. That's perfect. And then I can go ahead and start setting the fields here. So okay, and I also need priv dev and dev. Okay, great. I just noticed that oh no, never mind. I set that in a different order than I thought. Okay, great. Like, I don't think that would have been missing. Okay, that would not make sense. All right. This is, do I need to do anything else here? So that doesn't matter, that doesn't matter, that doesn't matter. RWSEM, that doesn't matter. That oh. Netif set real TXQs and dev1, and again the same for RXQs. Okay, cool. Dev ADDR len fa len. An Ethernet device, we're going to use a standard Ethernet MAC address size. We're just going to use a default random MAC address. Okay, so F hardware ADDR random, oops, dev, so we get a random address. Ostensibly, we can do something different later, but we're going to start with that. Hardware timestamping, that doesn't matter. Desk block size, that's fine. And then yada yada yada. Okay, what else do I need to do here? Net dev ops. So we need to do that. And do I need to do anything with ETH tool? I'm gonna forget about that one for now. All right, so this is going to be cndm net dev ops. All right, and then I need to define that structure, right? So this is going to be struct, I think static struct actually. All right, static construct. There we go. Static construct. Let's see. This is net device ops. Net dev ops. Okay, there we go. And this is going to be equal to a bunch of stuff. And we're only going to initialize a few things. So NDO open. This is going to be cndm open, right? And then we do this. I need to do at least 3 things, I think, right? So I need open, close, and start xmit. I think that's right. Yeah. Okay. Everything else is fine, I think, for the time being. Okay. All right, so I'm going to go ahead and create some stubs for these guys here really quick. So open, close, and oops, not that. Start port, stop port, open. All right, so static int open struct net device. Okay. What do I need to do here? So state lock, start port, state unlock. I'm just gonna turn 0 for now. Okay. Let me just take a look at what this is calling in the Corundum driver and see if there's anything I need to handle here. That RX control, no. Okay, so there is something about starting and stopping queues potentially. Yeah, I can't remember what the minimum is that we need in some of these functions here. So I think this is going to be netif tx stop all queues. Actually, let me just make sure. Oh no, this is fine. Yeah. Okay, so there's stop all queues and netif carrier off and dev. Netif tx disable dev. Okay, and then I think I need to do this in the reverse order, probably on open. So let me see here. Is there anything else I need to do? Read down radix tree. No, I don't need to touch any of this, I don't think. Disable tx ring. Yeah, I'm not going to bother with any of that for now. Set tx control. That's fine. Oh, so I'm probably going to have to do some of that. Okay. Well, all right. One step at a time. Right. So at the bottom of the read, or the setting everything up, we'll have to put the carrier on. Carrier on, right? And what else do we have? Okay, start all queues. Start all queues. Carrier on. Oh, there's also netif device attach. I'm actually not entirely sure what all of these calls do, but yeah, one step at a time. Right, so we got the carrier on, we got device attached, we got start all queues. So that is something else. We got a bunch of, okay, configured scheduler, direction RSS, that's fine. Set up TX queues. All right, let me see here. So we create CQ, radix tree, create, okay, open CQ, add TX, nappy add. All right, so we'll have to do one of those. Nappy enable. All right. Well, we'll start with this and just get it to create the device. The next step then is to actually be able to transmit and receive stuff. So, all right, so I've gone ahead and created the net device ops. We have the net device ops here. Yeah, I'm like basically trying to strip this driver down to its core, so we have like the absolute minimum stuff. Oh, I also need to create that transmit call here. So I'm going to go ahead and do static int ndm start xmit. And again, this is looking at the our skb. We have the skbuff, and we also have the struct net device and dev. All right, great. So we have that. Okay. And I guess I will. Well, what is the minimum that I need to do here? Okay. So I'm going to do dev k3 skb any kb, and then turn dev dx. Okay. Okay, so the idea here is that we're just going to drop the skb and report that we transmitted it just fine. So then I could do netdev info and dev got packet for tx. All right, cool. Okay. So this is a starting point anyway, right? Okay, so what else do we need to do? Well, we have netdev ops, and okay, let me take a look at netdev file again here. I need to do another one here. This is going to be this is going to be void destroy netdev, and this is going to be struct net device and dev. Okay, great. And free net dev and dev. Okay, great. And let's see, what else needs to be done here? I guess that's the main thing for the time being. Okay. Right. Unregister net dev. Okay, and I need to make sure that it's registered first. So that was one of the fields that I had in the other driver. Is I had a registered thing here somewhere. All right, so okay, great. So now I know if it's registered or not, so I can free it only if it is only if it has been registered previously. Okay, great. And then what we're going to do here is we're going to do destroy net dev, and this is going to be looking at end dev. It's going to be return error ptr ret, and right, this is return end dev, and this is going to be if something fails, we do that. Okay, so all of our common cleanup is handled down here. That's a little bit nicer than what we were doing previously. All right, what else do we need to do here? I think this is all looking pretty reasonable. There's not much else that needs to be done here aside from potentially freeing that. Okay. Or aside from potentially unregistering that. Okay, but then what I need to do here is after I set the net device ops, ndev hardware features. We're not going to support any features for now. And ndev features also 0. Okay, ndev min mtu, that's going to be min mtu, and ndev max mtu, set that to 1500, at least for the time being. Okay, so that can potentially be set to something else, but okay, one step at a time. Net if carrier off and dev. Okay, and then I finally go ahead and register this. So ret equals register net dev and dev. Okay, and then if ret, then dev error dev. What is this here? Net dev registration failed. All right, great. And then I go to fail. All right. Is this everything that I need here? Well, at least to register the net device and actually be able to accept packets from the kernel, I think this is kind of the minimal setup that we need here. Maybe there's a couple extra things in here, but we'll start with that. Okay, let me do a test build here and see if this builds correctly. Not that one. Where did I put that other window? That one either. All right, maybe it was one of these then. Okay, there we go. Make on that, we'll see what happens. Oh, I need to add that file, don't I, to the make file. So let me take a look at the make file, and I need to add Corundum net dev. Okay, great. I'll run that. What do we get now? Oh, all right. I probably need to import something. Explicit definition. I think I need to go back to here, and I need to import net device. I think yes. All right. Okay, that I think will work. All right, we still have a few issues here. All right, and what I'm going to do as well is move a couple of these definitions into the header file because these need to be called from elsewhere. So I'm going to move these two into the header file here. Move all that, and I'll do that and that. And let's see what that does. Okay, it doesn't have an NDO close. I guess NDO stop. Okay, I see. Wait, is it Alec NetDev or Alec EtherDev? Did that get renamed at some point? Oh, Ether device. Okay. I need to import something else. All right. Great. Not a big deal. Okay. Let's try that. Oh. I think that pointer error should be error pointer. Yeah. Okay. Oops. Clicked too many times. All right, and then registered. This should be all right. So I need to extract the priv. So that was going to be. What do I do there? Okay, so this is going to be struct. Oh, this is priv equals. This is net dev priv and dev, and then I can do priv registered. Okay, so that built. Now what I need to do is to actually go ahead and all right, so what I need to do now is add a net device entry to this, I think. Okay, Great. So that should work. And then what I will do now is go over to the main method here, and let me see here. So this is going to be, now I need to start calling these things here, right? So the destroy netdev here. I need to do that. Getting my programming languages mixed up here. So this is ndev. Okay, great. Destroy netdev ndev. I guess I can do the same thing here. Okay. If all of this is looking good, I'm gonna do, well, I guess ultimately this DMA buffer stuff is all going to be commented out, right? So I'm going to go ahead and comment that out for now. And then I'm going to go ahead and do, this is dev ndev equals, and run the routine to allocate the net device here. Create netdev. Yes. All right, so we do that. And what do we need to call with that? I just add the, oh, dev here. Okay, great. Okay, cool. So I do that, and then it's if what was the right way of handling this here? Where was the interface? IF. Okay, there we go. And somewhere around here, we're going to create the interfaces. Okay, great. If is error or null, dev. Right, then we will do what? Ret equals greater error dev ndev, and then we do go to, well, we're going to go to something, fail netdev, right? Probably that. Okay, cool. The fail IRQ. Yeah, so that'll be there, and then the DMA free coherent, I'm going to comment that out, and DMA free coherent as well, I'm going to comment that out as well. All right, so that's looking pretty reasonable. So that should be able to create the net device here. All right, so let's see if that works, right? Where is my, there we go. I will go ahead and copy that over. Actually, let me just make sure this builds correctly first. Yeah, okay, ndev was undeclared 212 and 238. Oh, I see. Okay, let's see if it's happy with that. Okay, so that looks probably reasonable. Actually, I'm also going to do one other thing. I'm going to comment out these to make sure I'm not accidentally doing something there. Okay, that looks good. All right, so now the question is, does it create a new network device? Assuming I can type my password correctly. Okay, try this again. Okay, that looks better. Now I'm going to go ahead and pull up the, here's a dmessage output here, and now I need the, where was my other terminal? Was it this one? Okay, there we go. Great. So I'll make, all right, it's built both files. Hey. So you can see we now have a network device here. And we're getting packets. So that's progress, right? We've gone ahead, we have a driver that is now registering a net device, and it's set up to actually receive packets from the operating system. So we're not doing anything with those packets yet, but we are actually receiving those packets. So that is a start. Now, the next thing I'm going to do actually is I'm going to nix my, my loopback and plug it into my desktop machine here. it helps a lot if you push on the retaining tab. Makes it a lot easier to pull the thing out. Okay, so I now have a 10G connection to this to my workstation machine here. So the next step here is to see if we can get the transmit and receive paths working, right? We're getting packets. We're getting packets at the driver level. Now we need to get those packets out the door. That's the next step, right? Can we get those packets out the door? And this is going to require putting a number of different pieces together. So, you know, one step at a time, we'll make it work. Okay. Let me see here. What is the entire process? So I'm going to go ahead and delete this for now. And we have code here for TXQ, RxQ, TXCQ, RxCQ. So I'm going to go ahead and in the NetDev creation code, we're going to go ahead and create all of those memory regions and load things appropriately into the device. So actually what I should do, so I'm not poking too much stuff here, is I'm going to go ahead and transfer over the bar fields as well. So we can always clean stuff up later, you know, but this is just, let's get this basic stuff working first, right? So in this case, I'm going to do all this, and then I'm going to do priv bar, bar dev bar, okay, and then I do priv bar len equals cdev bar len. Okay, great. So that does all of that. And now the next thing I need to do is this does that, and then free netdev. Okay. One moment. Let me take another look at the Corundum device driver and remember some of the sequencing stuff here. So for the net device, this is just unregistering the netdev. Okay. The queues are, at what point are the queues created exactly? I think, does that happen here? Is this talking about indirection table? Oh, right, because the queues, okay, for Corundum, the queues actually live somewhere else. The queues are registered under the interface, and then those have to get cleaned up separately. I think that's right. Maybe. Yeah, okay. So that has all the resources over here. Got it. Okay. So destroy the net devices, free EQs, free schedulers, free ports. Okay. Gonna take me a minute to remember what needs to be done exactly. Okay, so all right, during setup, how does this work? Enumerate registers, register blocks, right? So we have to find all those as part of the process of bringing everything up. We read all of the register layout stuff. And then we need to start bringing up the queues. Okay, so the first step is we disable all the queues, then we create the ports, then we create the schedulers, then EQs and the net devices. Let me see here. So for the individual queues, like for a TXQ or whatever. Oh, I see. It's only when you open the queue that it actually allocates everything. I see. I don't necessarily have to do that here. All right. That's, I think we'll be okay here as long as I try to keep things as simple as possible. Yeah, all right. So in this step, yeah, okay, so that's fine. So destroy netdev, this will take care of everything in the appropriate order here, as long as I do things correctly in the setup. All right. So here's how this is going to work. I'm going to go ahead and do basically what I was doing before here and create DMA buffers for all of the queues. So ultimately, this should probably be transferred over to a separate file and rehashed a bit, but we're going to go ahead and start with this, and then we'll see how it works. So this is going to be priv, and then we're doing this for all of these components. So TXQ, RxQ, etc. TXQ, and this is fail. Yeah, all right, great. So we have a TXQ regions. All right, so this is allocate buffer. So we've got TXQ region, and this one I'm just going to make this 4096 here. Okay, TXQ. I got to duplicate this 4 times. All right, do this. There we go. All right, so that's 4 times. So this is TXQ, so these are now going to be the RXQs. All right, RXQ, TX. All right, I got to do this individually for each one here because they're on the same line. TXCQ and finally RXCQ. RXCQ. All right, great. So that goes ahead and allocates all these, and then what I need to do is free all of them. It's always important to get this stuff set up early, so keep everything all organized. All right, so first thing we do is we unregister it, and then this is going to be based on CDev. This will be priv, and then this is going to be TXQ. I only do this if the TXQ region is there we go, if TXQ region. All right, great. So we do that, and then I do this 4 times here, right? Okay, great. So TXQ, RXQ. All right, RXQ. This will be TXCQ and RXCQ. All right. So what we should do is make sure this is not causing any problems, because this is just going ahead and allocating everything. Then we need to go set up the registers again, but that's that'll be straightforward. All right. All right, so let's rsync that. I will run make. Oops. All right. So dev, we need dev from somewhere. Okay, we'll try that. Oh, because I need to rsync that again. All right. Okay, there we go. Let me go ahead then, and I will rm mod. Oh crap. What did I do this time? Shoot. So something decided to blow up in my face here. What happened? Kernel bug, invalid opcode. Invalid opcode? Why would I be getting that? Well then, alright. I've crashed it again. Great. But I have no idea why this happened. Why would I be getting free netdev? IP free netdev. Why would that be causing a problem here? So it's well, this is perplexing. I have no idea what's going on here. Well, I'm going to reboot it and then try it with the updated driver, and we'll see what happens. Oh, it's completely borked. Okay, well, great. Great. Alright, that'll take a minute to reboot. While that's rebooting, let's see if I can make heads or tails of what I screwed up here. So, kernel bug at netcore-dev.c. Almost sounds like it's trying to call something. Why is it invalid opcode 0? It's like it's trying to execute something that's all zeros. Alright, let me just see. Is there anything else I need to implement here, right? So NDO open, yep. NDO stop, yep. So stop calls close. Alright, that seems fine. Start XMIT, that's fine. Get stats, not implementing that. Validate address, set MAC address, change MTU, IOCTL, devlink port. I don't need any of those callbacks, right? We just need open, close, and transmit. What could be going on here? Valid opcode. Well, if anybody's wondering what the motherboard model is, there you go. It's the X13 SEM-F. Nice. That's, I guess, useful. I guess the BIOS is relatively recent. Maybe I need to check on that, but that's not going to have any bearing here. Interesting. So this error is occurring under FreeNetDev. For PCI remove. PCI device remove. PCI remove. PCI. Alright, so PCI device remove calls this. Corundum PCI remove. This printout remove before all of this went down? Yes. Alright, so we got that. And then this goes into destroy netdev. And destroy netdev is this thing, destroy netdev. Pulls a netdev priv. Should be fine. And then we get dev, right? Then we call. Oh. Alright, yeah. I see what happened. I see what happened. We forgot to unregister the netdev first. Let's see, where is this? Yes, alright. Actually, I need to reorder this. So this should be the last thing that we do here. Okay. I register it, and then, yeah, and I'll do the netif carrier off as well there. Alright, great. Gotta do everything in the correct order, otherwise things are not going to work properly. Okay, great. So yeah, I don't know why that would have caused a kernel crash necessarily, but, well, you gotta do everything in the right order. So yeah, what would happen if you free it without doing that? I guess, I don't know. I don't know exactly why it crashed. I would have to go into the kernel source code to try to figure that out, but okay. All right, and then we got to do rsync the latest code. Make sure that's happy, and at the same time, I also need to fire off the Vivado. Okay, code is good. Let's reprogram it. That'll take a minute. All right, yeah, cleared my history, hasn't it? That one was what, BE? There we go. Hot reset, and this is not quite done yet. Give that a second. Okay. Okay, it's programmed, so we'll go ahead and reset it. Set it, and now let me go. Okay, that. Very nice, and now I'm going to go ahead and load the module, right? Okay, well. Okay. That's doing something useful now, maybe. Okay. Great. Great. This is, I mean, okay, it's not doing that much, but we are getting the packets, so that's a good start. And it didn't crash when I removed it that time, so great. And yeah, we have the network device created here, so okay, perfect. So this is allocated these queues. Now what I need to do is start setting things up. Actually, so I'm gonna allocate the buffers, and then we're gonna disable. Well, all right, then we'll just do the standard initialization technique that I had implemented before here. Well, let me see here. So I'm gonna go up to, where did I do all this init work here? All right, so I'm also gonna need to create all of the producer and consumer pointers as well. But yeah, one step at a time. Okay. Right? 1, 2, 3, 4. I think I have everything. Yeah, and then this is talking about descriptors. All right, great. So let's go ahead and paste this in. All right, so now is dev priv for all of these. Priv bar. Okay. Now instead of being rxq DMA buff, it's going to be rxcq region. Yeah, okay. So instead of DMA buff, I can get rid of all of these here. DMA ADDRT. These all go away, as well as that. Okay, perfect. And then what we can do here is the DMA buffer. All right, so let's select this DMA buffer. All right, so this is going to be priv, and this is going to be okay. I think that's right. So we register the 4 regions, we plug that in. Okay. All right, that's looking pretty reasonable. Let me think here. What else do I need to do? All right, I need to create the various pointers here. So I need producer and consumer pointers for all of the queues here. Go back over here and I do right. So each one of these I need a producer and consumer pointer. So these are going to be for I don't initialize it to 0 here, but this will be txq, right? And rxq. And txcq and rxcq, right? So here this is rxq and txcq and rxcq. Okay, very nice. Then what we can do is go ahead and set all of that up. So this is going to be all of these guys. So that gets set, that gets set. Okay, great. That is looking like a decent start here. So this will go ahead and configure everything. The next step then is to actually work on getting the flow of packets going towards the hardware. So let me think about this now. what we need to do is implement, I guess I'll start with the transmit direction, right? So we'll have start xmit called, and I need to do a couple of things here. So the first thing is I need to get the private data out of the net device. So this becomes ndev priv ndev, right? And then we need to do a couple of different things here. So let me take a look and remind me of how the TX code works over here, because there's several things that we need to do to make this work. And the thing to keep in mind is that we actually have to keep track of these SKBs until we're done. So there's going to have to be, there's basically sort of two parts to the descriptor ring. One of them is the DMA buffer that we already allocated. The second component is another ring which can keep track of the contents. That can keep track of the SKBs. So what I'm gonna do, let me take a look. What did I have to put into this previously? How did I do this before here? Okay, so SK buff, obviously, and okay. I'm just trying to remember exactly what needs to be done here. All right, so I need to create another structure. Need to create another structure here called so this is going to be, so there's tx info, and this is going to have to hold a DMA ADDR-T, DMA ADDR, and it's going to have to hold a like I said, sorry, U32 len. All right, I think that's right. I don't need that. I don't need that. Oh, and I need to store the SK buff. Struct SK buff KB. All right, great. So I need that, and I think for RX, well, one step at a time. We'll do TX first, and then we'll figure out RX. All right. So, oh, I need a semicolon here. Okay, great. Then what I'm going to do is I'm just going to go ahead and define an info ring here. How did I define this here? All right, and I also need RX as well. So TX info, RX info, great. And then I also need to create a, backing for both of those. So that's pretty straightforward. Let me go take a look at, oh, where is that created? TX ring size, no. Oh, I guess this is going to be created over here. And we have like the TX ring, When I create the TX ring, I also need to allocate that. Okay, so allocate the buffer, and then I also need to allocate the info ring. Okay, there we go. So allocate info rings, and what I'm going to do here is priv tx info, and that's going to be set equal to vz alloc size of priv tx info times, but that was, we're doing 256 entries for these things, right? And then it's a gfp kernel. All right, great. And then we need to do the same thing for rx as well. Yeah, rx info. All right, and then if this fails, if not priv tx info, then we do the same kind of thing where we return enomem. because that operation failed. So I do that, and I do it again over here, right, for the RX info. Oops. All right, TX info, RX info. All right, so I have all of that, and then again, I need to go down here if priv TX info. Then this is going to be doing what? Check on this here. This is just KB free. All right, great. So we do that, and then we do this again for the RX info. I'm going to need both of these later. All right, so we have created the TX info and the RX info rings. I think we're getting close to being able to actually try to send a packet here from the kernel. As you can see, there's a lot of boilerplate that you need for this to work. And eventually, you know, all of this is going to have to be kind of rehashed and reorganized to make it a little bit more organized. But this is a good starting point. All right, so we fire off the, where was this? Create netdev? No, not create netdev. There's probably more stuff I need to do here. Yeah. All right, well, one step at a time, right? Yeah, okay. So let's take a look at this then. I get the SKB, right? So shared info. Well, all right. Let's just try to figure this out then. All right. So we don't need to bother with that. We don't need to bother with that. Have the ring. We have the ring. Oh well, no. I'm not even bothering with that for now. Okay. Netdev warn. Right, if we have a short frame, then that needs to be dropped. Is this the correct thing to do for how does this work? TX drop count, key free any netdev TX. Okay. Oh, is that right? Okay, yeah, we want to make sure we're not trying to transmit a packet that's a problem. All right, so I should go ahead and add that. All right, so this is if skb len is less than fh. If the packet is really short, then we just want to drop it. Netdev warn. Why did I do that? That's funny. All right, so netdev warn. Dropping short frame. I mean, I guess the alternative is it can be added out, but anyway. Go to TX drop. All right. TX drop. There we go. So if something fails, we go to TX drop, and we have a nice way to bail out here. All right. So we have U32 cons pointer, and we also have a. What else do I need here? Okay, and then also do the U32 index here. All right, so we need to know where we are in the ring. So what we're going to do is we're going to do cons pointer read once priv. This is going to be txq cons, right? And then what do we need to do here? Index equals we read the producer pointer, and we're gonna AND that with a mask value, right? That will tell us where we are. Oh, we need to do size mask. Okay. I'm just gonna hard code that for now. That should be the correct value. More stuff for the old cleanup later. In fact, I'll go ahead and annotate this one. Okay, so that tells us where we are in the ring. Now that I didn't really talk about this before, but the idea is with the producer and the consumer pointers, they're fixed at 16 bits in the hardware, and they will continuously increment and overflow. So we just need to mask off the bits that we don't need when we need to look up something in the queue. Right, so this gives us the index into the ring. And now I need the TX descriptor. So it's going to be a struct desk. So that's your descriptor, right? So your descriptor, this is going to be equal to oops. So we're going to cast that from the priv tx q region, right? Plus index times 16. So this is how we get the descriptor that we're going to use. Okay, great. And then the tx info, this is just the priv tx info x, simple. Okay, so we got both of those. Now, let's see. Not doing any time stamping, not doing any checksumming. We haven't, we don't need to linearize anything. Right, so then we need to map the SKB. So at this point, we have the SKB, but we can't really use the SKB because it is not yet mapped. So what we need to do is, let me see here. Remember how this needs to work. Okay, so I need to do 232 len. All right, so I do len equals skb. All right, actually, I guess in this case, well, this is fine because that I believe will be equal to the packet length. But all right, anyway. DMA ADDRT. Oh, is that fine? Yeah, all right. I will do that as well. So I have len DMA ADDRT, DMA ADDR. So we need to get the DMA address, right? So DMA ADDR equals DMA map single. Then we need dev. Do I have dev? I don't have dev, so I need that. Struct device dev equals priv dev. All right, great. DMA map single dev. Let me see here. AB data and len and DMA to device. All right, great. So we've gone ahead and we've mapped it. This gets us to mapping. Now, if DMA mapping error, we're going to do dev again, and then DMA ADDR. Then this is going to be doing what? We're going to go to what do we need to do on map on the fail? If it fails to map, I guess we don't really need to do anything. If the mapping fails, then we do that. All right, cool. Move this up, and then this is going to be an error. The mapping failed. That dev error. Okay, that'll be correct for that. All right, great. So we get those, and then we do tx desk len equals len CPU to LE32 len and tx desk DMA ADDR. Is that right? I think it's DMA address, right? Or it might just be address. Or my header file is. Oh, it's right there. Okay. And for the descriptor, we need the, yeah, just the address. Okay. ADDR equals CPU to LE64 DMA ADDR, and then I need to do tx info skb and tx info len for that as well, and tx info DMA ADDR equals DMA ADDR. We got to jump through a few hoops here because we need the DMA address and the length later on when we want to free this. I don't actually know why you need that, but it's part of the Linux kernel API, so we have to save that. All right, so I think at this point, this will be putting the descriptor into the ring. And at this point, even though the whole setup is not quite complete, we may actually be able to do something. There's actually one other thing that I need to do before we make an attempt to run this, and that is that I need to clean up the ring afterwards. So, let me see here. Where is the code that I need to look at for this here? So, because this maps it, but at some point we need to unmap it. So we need to look at, what's in the queue, and based off of that, we need to go in and clear stuff out. So let me just see here. I think this is how this is going to work. Wow, int process execq device and dev. Okay, so the idea here is we're going to be able to go through the queue and clear out anything in the ring that needs to be cleaned. So I'm going to start out with basically something that's really only appropriate for hang on a second here. There's a free TX buff, free TX desk. Oh, okay. Yeah, all right. So I will need that eventually. I'm just going to, for now, I'm just going to do that here. All right, so free TX desk. And then there's another one for free TX buff. Okay. That what I need here. Free TX buff. Like, how much boilerplate code do I need to create just for this to work here? Okay, so that's calling free TX desk for each item. Okay. So what I need to do here is write some code which can go through and clear out anything extra that might be lying around in the queue. So this is going to take the private data structure, and it's going to go through and attempt to free everything out of it. So let me think here. U32 index. All right, great. Okay, so now I do while. Let me think for a second here. So this is going to be using the consumer pointer and the Oh, what is this call doing exactly? Okay, I see. While priv, let's see, this is going to be txq prod is not equal to priv txq cons. All right. This is going to loop over everything. Okay, and let me see here. This is going to be doing index equals priv txq cons, and I gotta fix that later. All right, and I also need the index is specified up there. I don't know why it's giving me a red line, but whatever. All right, so this is then going to call the free descriptor on that. So, oh, okay, so priv and index and v0. Okay, and then I need to do priv txq cons, increment that, and that. Okay, great. Okay, and then for the TX descriptor, I need to do the same thing, need to accept the private data, So we have all the pointers to everything. Index and okay. So we're gonna do so we need the TX info structure, and this is going to be priv TX info index. Okay, and then I get this struct sk buff kb, and this is equal to TX info kb. All right, and let me see here. DMA unmap single. This is then, all right, so I need to do struct device dev equals priv dev DMA unmap single with dev, then DMA unmap, actually TX info, so DMA ADDR. All right. Oh, there's a couple other things I need now. I need TX info DMA address, TX info len, and 0, right? Or DMA to device. Yeah. Then DMA unmap ADDR set TX. Oh wait, no, never mind. All right, so this is going to be TX info DMA ADDR, set that to 0. All right, great. And then nappy boom skb skb nappy button. So this one is basically returning the skb to the kernel. Okay, I think that's everything that I need here. I need to make sure when this thing is being closed down that that this thing gets flushed, basically. So when would I need to call tx buffer? Yes, think about this here. So I need to call this. Is there any time I wouldn't want to call this? All right, so here's what I'm going to do actually. I'm going to go ahead and rearrange these guys. This down here. Okay. And if the info ring is allocated, then I will need to go clear it. There we go. All right, so this I can do cndm 3tx buffer. Okay, let me actually add one more thing here. I'm going to do an unmap, just for making sure things are happening in a reasonable way, and if something fails, then it's quite important to be able to track what the story is here. So I'm going to go ahead and I'm going to add some debug calls here. So I'm going to do write desk index %d length len %d. All right, so in this case I now do index and len. All right, and this is going to be free desk index. Okay, great. Okay, is there anything else I need to do here to make sure that this is skb? Yeah, I guess this seems fine. All right, so let's just think about this for a second here. When this gets called, if producer and consumer are the same, then nothing happens. If producer and consumer are different, then it's going to try and free at that particular index, and it will increment consumer. It'll do that until they match. Okay, that seems reasonable. All right, now let me actually, I need to do one other thing now that I'm thinking about it here, because this could be a big problem if, yeah, this could be a big problem if this overflows to queue. So when I create no, not when I create the net device. When I transmit, I need to make sure that we're not going to overflow the queue. So let me do that real quick. Let's see, where is this going to be here? That's map SKB, start transmit. Where is the check to see if there's, oh, I see. Okay, so, oh, I just realized that I've screwed something up already here. I need to increment the pointer, don't I? Right, so I've written the descriptor. Now I need to do priv tx prod plus plus. Now I do need to write this to the hardware, so I'm going to go ahead and add the call for that. But I might comment it out for now. No, I'll go ahead and actually make the write. So the updating of the tx production pointer, or producer pointer, is here. So I'll go ahead and copy and paste that to start transmit, right? So we update the pointer. And now I need to do if priv txq producer. Oh, let me see. How do I know if the ring is full? Let me see here. Is ring full is producer pointer minus consumer pointer. This is going to be greater than or equal to, I'm going to make it 128 just to make sure there's some buffer. Yeah, because there's a full size value which can potentially be specified separately. So we're going to do that for now. If that is the case, then we are going to do a couple things here, right? We're going to print out netdev info ring full. Okay, and then we need to stop the queue. Netif tx stop queue. Oh. I need to take a look at something here. So this netif tx stop queue, is that just taking an index, or is that taking like some sort of a data structure? And let me just take a look at something. So when this thing is allocated, the txq, what is that set to? Oh, I guess there's actually a couple of other things I need to do here. So I'm going to move this one down, right? And before I do that, I do a DMA WMB, right? That's super important. Yeah, okay. I need to make sure that the hardware is seeing something consistent. Yeah, okay. That seems reasonable. Okay. Great. Oh, I was going to check on. I'm still looking for this here. Where is that set? Oh, maybe this is set. At dev get txq. I see. All right, let me just make sure I'm doing everything correctly here. So I need to go under, this is txq under the ring structure. Is that a, where is that specified here? All right. So this actually needs to be specified somewhere. All right, let me see. This is, yeah, because this is actually a data structure here. So priv txq. All right, and this needs to be set somewhere. Let's see, I need to go back over here and I need to specify the txq. All right, oops. Struct netdev q txq. All right, so there's that, and that needs to be set down here somewhere. All right, so when I do, I guess, was it after registering the net device? I don't know. All right, let me see. It's gonna be, okay. Dev, so the TXQ is set here. In the teardown, I don't know if I'm doing anything with that. All right, so I guess I need to put this on the start port. I open this, I need to go ahead and assign the queue. All right, cool. So tx, no, priv, I need to get that priv out of here, don't I? So let me copy that from over here. All right, so now I have the priv available, and I'll put it here as well, just sure. And what I need to do is priv txq. This is set to let me see here. Okay, netdev get txq. And dev 0. Yeah, all right. Oops. Okay. Let me see. Where's the local build of this thing? Oh boy. All right. Something's not happy about something. Oh. Dev priv line. Okay. So this has to be fixed in a few places. Okay. All right. So let me see here. Unused variable priv. That's fine. Tx free desk. What's the issue here? No previous prototype for tx free desk. Incompatible types. Oh, so I just need to do that with a, all right. That. Okay. Let's try that. Undeclared line 32. Okay. That's fine. Valid application of size of to incomplete type. But why is that an incomplete type? Oh, because I didn't specify it. Okay. RX info. Yeah, that would make a difference. All right. Okay, that's fine. No previous prototype. No previous. What are you complaining about? No previous prototypes. It's not defined static. All right. Well, whatever. I'll just ignore these for now. Start transmit TX info undeclared. Start transmit. So the TX info is also undeclared. All right. Well, then I will go ahead and create that. Okay. Priv TX info. All right. So 84. I have a similar problem. I need to add another Need to add a reference there. All right, and then tx desk len. Oh, I think that's just desk. All right. Well, all right. I'll just call it tx desk instead of desk. Tx desk. All right, great. So that should fix that. And then there's a CPU 2. I have another typo. Oh, CPU 2 LE64. All right, cool. Okay. Great. So let's see then if this decides to do something useful. High probability I've messed something else up. So what's the over and under on this thing crashing? 50% chance it works? I don't know. Okay, so RM audit. Okay. Now I will insmod it. Something is happening. That's good. Let me see if I RM mod it. Yeah, alright. So we were good until I tried to RM mod it. Okay. Yikes. Stock W free. So something underflow use after free. Uh-oh. Free desk index 0. What? Oh, wait a minute. Yeah, oops. That was stupid. Yeah, I knew I would have missed something. So let me see. What do I need to do here? I think I just at the where is this? To go down here, I just need I just need to do netdev-tx okay here. Alright. That's embarrassing. But at least something simple, right? And it is completely hosed. So let me reboot it again. So it worked on load, it crashed on unload. Okay. Let's give that a minute to reboot and then we'll see. Okay, it'll take a minute for that computer to come back up again, but hopefully that's the only mistake so far. So I think we're up to 3 crashes so far, right? But who's counting? Yeah. Yeah, servers take a minute to reboot, so alright. Not a big deal. But yeah, you can see it is starting to load packets into the frame, into the queue here. Alright, so now what I need to do is I have a network namespace running on here. This is on my local machine here. This is at the other end of that 10G cable. So what I'm going to do we're going to take a look at any traffic that we see coming from there, which should be interesting. Let me also go ahead and pull up, I need to run Vivado again to reload that card. Are we up yet? Yes, we are. All right, cool. All right, we're up. Let me go ahead and program it. Yeah, for all of you people out there wondering about, why I never do the PCA device development on my workstation machine, well, this right here is exactly why. it's very easy to make a mistake that completely crashes the machine in an irrecoverable way, and you got to reboot it to recover. So yeah, it's not hard to do that. But yeah, if it's a different machine, you can just, you know, yank the plug and reboot it, and then everything's fine. So, although I guess systemd complains bitterly about its log being screwed up, but whatever, that doesn't matter. All right, so it's currently programming the FPGA. All right, so I'm going to go ahead, pull up dmessage, and then what we can do is let me make sure this is rsynced. A lot of things that need to be done in the correct order, right? Okay. What do I need to do? Oh yeah. We grab the PCIe ID, it's BE, right? Okay. Sudo we'll reset the card. Card is reset. Build the driver. Be annoying to run the old driver. Okay. And well, we got a couple of things. Oh, I think I might know what's going on here. And the reason this is being slow. Okay, so this freed all the descriptors 0 through 21. Hey, that's perfect. Okay. But yeah, we got some useful traffic out of here, it looks like. So let's see. The first couple were like 28. 8. Oh, I guess that's the interior length. Okay, I'm gonna do one other thing here. Let's reset. Let's clear this out here. And I am going to okay, I need to make sure this is not attempting to do any not DHCP, DNS lookups. Yeah, we can actually get an accurate picture of what's going on here. All right, so I'm going to insmod it again. Then I'm going to rmmod it. All right, so we got a handful of packets. The first packet was really big. That actually looks reasonable, right? So that reported a length of 325. Let me pull up a so this is 140 1 3 4 5. So 145 is 325. Hey, what do you know? That is exactly correct. The next one of those has 50. 1 2 3 4 5 6 7 8 9 10. So that would be 0x5a, which is 90. Oh, very cool. And then this one is a couple of short. It's 4 bytes short, so that puts you to 86. So hey, there we go. We are now successfully sending packets, and they are being sent on the one end. They are showing up on my workstation machine. So packet transmit path from the operating system on Linux on one end to Linux on the other end. It works. Now, to some extent, we only have a quarter of this implemented, right? Well, all right, not a quarter. What do you want to call it? About 2/5, right? Because there's basically 5 main things that the driver and NIC need to do, right? You have the initialization, and then you've got the TX, forward path for the data, the TX, cleanup path handling the completions. You've got the RX forward path for filling the buffers, and the RX completion path for handling the completions, right? So you got 5 things that need to be done. I've got 2 done and 3 to go. So, okay, that's a pretty good start, and for a day and a half worth of work, that's pretty good progress. All right, well, let's see how much more I can get implemented here. Right, so we have, and we got the buffer freeing. So basically this will work until the TX buffer fills up. Once we implement the TX completion queue handling, then it's going to get a little bit more straightforward, I think. So Let me take a look and see if I can implement that, and we can get that running under the purview of the interrupt handler. And then we can see if we can apply this to the receive path. So one step at a time. So process txcq. I need the net device, and I also need the int nappy budget. There's a bunch of other stuff that I'm going to have to implement for this to actually work correctly. But yeah, one step at a time. Let me see here. Oh, where is this process txcq called from? Let me just check on something really quick here. So this needs to be called from pollcq, and pollcq, where is that called from? One moment. It's been a while since I've looked into exactly how all this setup stuff works. Oh, is that handled here? Let me see here. Oh, this is the stop ports, but if I start ports, let me see how this works here. Netif nappy add tx. Yeah, okay, so that's when we call the poll txcq. Got it. Okay. Okay, so that has the nappy for the tx. All right, nappy enable armcq. All right, so now the question is, how do we get the interrupt connected to that? The only reason I'm able to go through this pretty quickly is because I spent hours and hours and hours reading over Linux kernel source code to figure out what needs to go where, and now I have a driver that I can use for reference to figure out exactly how things need to get called. So yeah, this will take probably a few more minutes to figure out, but this is looking pretty good so far. Assuming I can remember how everything is connected. The IRQ handler, atomic notifier call chain. Oof. All right. How do we add stuff to the chain? This is called with, well, it's not that. Atomic init notifier head. Okay, but we're not doing that. PCI IRQ vector. Oh, this is init PCIe. Okay, so if I do PCI IRQ vector, oh, but this is calling back to this. So, all right, so that's got to be handled at the net device level, perhaps. Let me see here. Oh, so there should be, I thought there was an kind of a top level IRQ handler function. Maybe there isn't. Was it at the interface level? Oy, oy, oy. There's a lot of pieces that are all interacting here, and there's a few things that I am forgetting exactly what the process is for connecting all the pieces together. ARMCQ. Oh, maybe it's on the CQ processing actually. All right, so CQ. I guess we might as well just pull this up. Create CQ, open CQ. All right, ARMCQ. Okay, mconnect EQ attach CQ. Oh, right, because this also has the EQ sitting in the middle. Just to complicate things. Okay, so EQ. So there's a process EQ. Where does that get called from? It gets called from here, EQ int. And this has notifier block action and data. Okay, right, because this gets put into the notifier chain. Okay. Yeah, there's quite a bit of complexity here in this Corundum device driver to handle, you know, variable numbers of interrupts and attaching stuff onto interrupts and stuff. So just to keep things simple, where did the IRQ code go again? All right, so I have the IRQ handler already. That should be sitting. Oh wait. Oops. What did I just do? Okay, there we go. I have the IRQ handler already. Where did I put it? Here's the IRQ handler. I'll just call this IRQN. Yes, all right. So I have the IRQ handler. Then what we need to do is this needs to call into what? Okay, so for this it calls into the event queue, EQ. I think it's a little bit simpler than that, right? Because I'm trying to remember where this is handled. At some point this needs to get, at some point there's a call into nappy to actually trigger the path, and I'm just trying to remember where that is. Is that here? I think it's here. Alright, it's going back here. So EQ, when the EQ is processed, what does it call? This calls CQ handler. Okay. Okay, I see. So if I go into the CQ, when this is set up, a handler should be defined somewhere. You attach CQ. Where does the handler get set? Maybe it doesn't get set here, actually. Maybe that gets set in like the RX or TX. Boy. Open RX ring. So there is a CQ that's specified. Okay, alright. There we go. RX IRQ. Okay, so that is eventually called. Where is RX IRQ? Alright, so that, okay, that gets called with the CQ. Alright, there we go. So eventually we need to call nappy schedule IRQ off. That is what it is. Alright. And I think I can just do that from the top level. So I'm gonna do this is not going to be the most efficient thing ever, but that's not the point. We're just trying to get it working. Right, so what I need to do now is I need to add to the main Corundum device here, I need to add a nappy structure to this, I think. Let me see, where is this defined? This is in the CQ, and the nappy is a nappy struct. Alright, cool. So that goes into priv, and I need to create, do I need one or I need two? I'll create two. Nappy, I think, stands for either new API or networking API. And this, the way the process actually works in Linux, when everything is set up correctly, and in this case it's not really going to be set up correctly, but whatever, we can deal with that later, is the interrupt basically causes the NIC to transfer into a polling mode. So the idea is that you will set up everything to start transmitting, start receiving, whatever. You'll enable interrupts, and then when the interrupt fires, then it switches over to the Linux kernel polling. So it'll poll for some amount of time using a thread that's not as part of the interrupt service routine. We'd spend minimal time in the interrupt service routine. We just kick out of that into a thread, and then the processing takes place in the thread. All right, so I've created these nappy structures here. Oh wait, they're not pointers. They're just structures. All right, cool. And now I need to I need to make sure these are properly initialized and everything is set up. So I need to take a look at CQ. Does anything here happen to nappy? No. All right. There's one other thing that I need to do here, I think, just to make sure, is actually these should both be bool, but this is fine here. Okay, so port up here. This one, yeah, basically this is going to be the last thing that happens here. Priv port up is set to 1, and over here we get priv port up set to 0. Okay, great. So I have that, and now over here I'm going to do if dev port up. All right, then we can run the nappy stuff here. I just want to make sure that things are not getting called when they're not supposed to be getting called. So That's kind of the most important thing here. All right, so in the netdev here, is it the netdev where this is set up? Maybe it's actually, oh, I think it is in netdev. All right, cool. So I need to do the netdev setup for at least the TX sides, right? Not necessarily both. Go back to netdev. All right, so for TX, so TX start all queues, TX carrier on. All right, I need to go a little bit further back here to create all of this stuff. All right, so create CQ, read lock, tree lookup, open CQ. All right, so netif nappy add TX. So I need to do that. Netif nappy add TX. And this is going to be ndev and do priv tx nappy. All right, and well, that's just whole txcq. Okay. Okay, so I do that, and then I need to do this again for rx. Okay, so I've got rx cq txcq, and then I need to do nappy enable. Again, the same thing. All right, and this is going to be rx nappy as well. All right, great. And I'm going to comment out. Oh, this is going to be rx probably, right? Yeah, so I'm going to comment that out for now. I will double check on that. Nappy enable, is that the only reference to nappy? I think so. Arm CQ, create CQ ring, that's fine. Yeah, that looks reasonable. That looks reasonable. All right. And then tearing down, we need to do some similar stuff in terms of disabling nappy. We need to do nappy disable and nappy del in the reverse order of what we did here. So we'll do that. Do nappy disable. Nappy disable and nappy del. I guess it's not TX or RX, right? Oh, and I don't even need the ndev when I do that, right? So I just need the nappy reference for that. And I do this both for RX and for TX here. So this is RX nappy. All right, RX nappy. All right, great. And I'm going to comment that out for now. We're just going to do TX first. Okay, great. So I have that. Process TXCQ. Now I need to do int cndm pull TXCQ. All right. So the idea behind this one is this gets called by the kernel. And I need to do one other thing, right? I need to go over to, where was that? I guess this was in, okay, there we go. Yeah, nappy schedule IRQ off. Okay. Oops. Nappy schedule IRQ off. This is going to be dev ndev tx nappy, and then again for rx nappy here. Rx. All right, but comment out the RX for now. Okay, great. So we nappy schedule IRQ off. We do that for both of those. So that's what happens when the IRQ fires. Then we schedule nappy, which will then do the processing subsequently in a separate thread. Now, ostensibly, what we should be doing is disabling interrupts in the meantime. I would have to look up how to do that with the with MSI interrupts, but I think this should be fine. Nappy pull RX CQ. All right, so now I need to do these guys, which is struct nappy struct oh, star nappy. All right, and then int budget. Okay, great. Now what do I do here? Struct priv equals container of happy struct what is this here? Priv this is tx happy. All right, great. So that gets me that. Int done. All right, so done equals process txcq, right? Priv and dev budget. Okay. If done equals budget, then we return done. Else we do happy complete, happy, and then we would rearm interrupts. Return done. Okay, here. Enable. Okay, cool. So that's to do. I think this is going to work well enough for now. We need to do this for TX and for RX, but you know, one step at a time. All right, now we get to the TX CQ processing here. Let me actually just take one look at whether or not this thing compiles. I assume that I will have some adjustments to make here. I think at least I need to put this poll TX CQ as no member of TX. Wait, what happened? What is this? Struct, oh, struct net device. Ah, I see. I need to do one more thing here. All right. Let me see here. I need to get this this priv back here from the net dev. All right. So what we're gonna do is set that. That's going to be coming from dev. Again, this needs to be cleaned up, but what are you going to do? All right. Okay. All right. So this one was undeclared. So I need to move the poll txcq up into here. Well, not really move it, but at least put a copy of it here so we can call it. All right. Okay. That at least compiled. All right, so what do I need to do next here? I need to do the process txcq. So what do I need to do for that? Let's see here. So what I need to do now is everything is going to be coming in order. So I need to get private data structure and potentially also the device minimum. And this is going to return ultimately done, which is going to be int. All right, so it's done, and then it's going to be oops, done 0. All right, great. Let's see. Is there any? I don't know what's going on with that. Okay. All right. So here's what we're gonna do. We're gonna do while done is less than nappy budget. All right. And then in this case, we're gonna do CPL equals C and NML. Oh, struct pointer, and this is going to be coming from the priv txcq buffer. Hang on a second. Region address plus. Oh wait, no. txcq region, yes, plus index times. Oh, let's see. I need to do two things here, right? I need CQ index right? And U32 index. All right, so CQ index is going to be set to what? Oh, this is going to be priv TXCQ cons and that later. All right, so TXCQ region plus CQ index times 16. That's the size we're using. If all right, so now I need to edit that structure here to actually make this 15 and then have 8 phase at the very end of it. All right, so CPL phase and okay, cool. And if this is equal to EQ cons, okay, here's what I'm going to do actually. I need another one of these here. So CQ cons are priv TXCQ cons. All right, so I have that, and then this is going to be the CQ cons and that. All right, so CQ cons and that's again, whoops, another basically to do at this point, but there we go. All right, so that, if that's true, then then we're done basically. All right, so then we need to do DMA RMB, right? And then we can start working on this here. So so index equals actually, I guess what I need to do now is I need to have the consumer pointer as well. So that is going to be I'm going to do, let's see, cons pointer equals priv TXQ cons. Okay, great. So the index here, this is going to be cons pointer and your FF, so we get the index into the ring. Okay, looking at the RX stuff here. Hang on, let me just make sure I'm looking at TX here, so I'm not confusing myself any more than necessary. All right, so that, and then we fetch that, we get the ring index. Okay, so then we can get the TX info, and this is the TX, oh, sorry, not TX ring, this is just priv TX info index, right? So that gets us the index here. And then we free the descriptor, right? Actually, do I need to do anything with this? Maybe I don't even need the TX info entry, right? So I call free desk, right? And then I do done plus plus, and then I do CQ cons pointer plus plus, and we do cons, yeah, cons pointer plus plus, and yeah, okay, now at this point I do priv TXCQ cons equals CQ con pointer, and then again with the regular Q, right? I put that pointer back as well. Okay, great. So, and then do I need to do anything else? Process ring. Okay, yeah, no, I think this fine, right? Probably. Yeah, all right. I think this is going to be good enough. Okay, let's see if this works. I think I have everything in place here, but we'll see. All right. Okay, let me just make sure it builds here locally. Nope. It complained about that. Oh, free. That should be TX descriptor. All right. Unused variable dev. All right, so we don't need that, do we? Okay, we'll get rid of that. Oh, there's also a nappy budget. Needs to get passed in here, apparently. Okay. I don't know why I'm handling these differently, but anyway, all right. So then I put the nappy budget here. Okay, great. We don't double check why that's passed in here. Oh, because it gets passed through the nappy consume skb. Right. Okay. Cool. And then CPL is undeclared, so I need to create that as well. All right, so I take this, and with the that goes up here. Okay, this is gonna work. Okay, actually, I also need to add the length to that completion record, right? So the length I'm gonna have. Where did I put the length in there? I think it was the same as before, right? So I do 4, and then LE32 length, and then this is gonna be 3? No, 7. Okay, there we go. 4, 8, and then another 8. All right, yeah. Reserved 2. Okay, cool. All right. All right, all right, all right, all right. Let's see if this does anything useful this time. Okay, that's Vivado. That's fine. Okay, I need that. Need that. And I need... All right, where is my... There's that. And then I need to rsync it. Yes, perfect. Okay, rsync it. Very good. And then I build it. That does not make sense. Uh-oh. Uh-oh. So why did that happen? It didn't crash that time, but that didn't do what I was expecting it to do. Somehow it did a loop around something way more times than it was supposed to. So the question is, what happened here? Oh, I guess there's another thing that I need to do here. I need to make sure... okay. I think I know what happened here. I think there may be an assumption that the ring is empty when it actually isn't. So there's a break here. So what happened? In other cases, something didn't quite go according to plan. Okay, so this wrote desk index 0 length 325. Then there was an interrupt. And then this somehow freed a whole bunch of descriptors. It freed all the way up to descriptor 63. That doesn't make any sense. Then it wrote a bunch more packets. And then I killed it, and yeah. Well, this probably created a leak then if these didn't get freed, but why did this happen? This is what I'm trying to figure out now. All right. That is really weird. Okay, so this one, x CQ region times CQ index. Oh. All right. So actually, I need to take a look at this here. So CQ index is. Why did I do it that way? Oh, I see. So CQ index. Okay, but I could just make that the first line. Yeah, all right. Okay, so I do that. I get the CQ index, right? So I increment that. All right, so it did that until it ran out of budget. All right, so it didn't even just repeatedly. Okay, yeah, that was not good. Okay, but this is more reasonable. So I get the CQ index. I get the index. That looks fine. All right. Well, so that would have leaked something, but what are you gonna do? Well, actually, no. So this freed 0 through 20. Maybe it's okay then. This actually seems to be working fine now because we can see. Is this, did I leave this running? I don't think I left this running here. Oh, I did leave this running. Okay, so this is actually still going. And you can see that this actually seems to be doing what it's supposed to do, right? It got a packet for TX, wrote it to index 0, and then freed index 0. It got one for index 1, and then freed it, so on and so forth. Got one for 2 and 3, freed 2 and 3, so on and so forth. So this seems to be doing what it's supposed to do for the transmit path. Okay, great. I guess we have two pieces of this working now. All right, two pieces working of the fast path. Two to go. Right. Let's think about this then. I actually can't remember how I did this in the very early version of Corundum where I wasn't doing the whole memory page thing. Whatever, we'll just do pages because I'm more familiar with that. The idea is that we can attach those pages onto buffers when we hand them back to the operating system. Right, okay, so this is looking pretty good. Everything seems to be doing what's supposed to do. Actually, wondering if there's anything I should do here to try and like encourage this to loop around the end, right? Well, it will eventually. I think what I could do, I'm just gonna make an attempt here. If I mean, this is obviously not going to ping if I run this, but oh, all right. This is in a network namespace. How can I forget? Was it this one? This one. Yeah, there we go. Oh, it doesn't have anything assigned at the moment. Okay. What I'm trying to do now is to get this to generate a bunch of packets and loop over the end of the buffer just to make sure that everything is working correctly. Not sure if this is helping though. Yeah, all right. Well, I'll just let that run for a while and we'll see what happens. Okay. In the meantime, I'm going to see if I can get the receive path working. So, there's two pieces for this, right? We need to do two things. We need to start allocating pages that can be assigned to TX or to RX. And what we do is we fill the RX ring with pages, and then we need to receive data into those pages. And Houston is back, so been napping all day, and I guess he's ready for some more pets. So let me go ahead and turn the cat cam on. There we go. There's Houston. All right, great. Let me go back to where I was working here. All right, so I need to make sure that we have all of the required stuff in the RX info page, and then we can allocate everything appropriately. All right, so let's go back to here. For the RX info page, what do I need? I do not need an SK buff because there is no SK buff for RX, but I do need a page. There's your page. Page order, page offset. Page offset. I can't remember what that's for. DMA address and length. All right, so I think that's what I need. Do you have the TX info? You have the RX info. Okay, great. Now what I need to do is I need to go ahead and implement what we need for RX. So there's two pieces associated with this, right? We need to fill the ring. We also need to be able to empty the ring as well, right? So we need to be able to free TX descriptor, free TX buffer. All right, so I need to define several different functions here. So we have all the TX stuff. Now we'll start with all the RX stuff. I'll put this down below TX here. All right, so let's see here. Void. Oh, I'm actually going to make a copy of the TX code for the moment, and we'll make a couple of adjustments to it. So we need a free TX descriptor, and we need to free TX buffer. All right, so free TX. So, but this is going to be RX, not TX. Go ahead and get this fixed here. Okay, RX. Okay, I think the RX, I think this might actually be done here, right? Because looking at these guys, RxQ, yep, okay, yep. I think this is all correct. Great. I go to free RX descriptor. So priv index, well, there is no nappy budget here, because there is no SKB, right? Okay, so we have the device. Then we have the RX info, right? We pull that, and then there is no SKB, so that goes away. Free descriptor, this is going to be RX descriptor, and I should actually annotate here for TX that we're freeing the TX descriptors, right? So we're going to leave all that in. All right, so free RX descriptor. Where was that? Where was I working on that? Okay, there we are. Free RX descriptor at particular index. All right, so now we need to do a DMA unmap page. Unmap page. So this is with the device. We have the DMA address, length, and DMA from device this time. And then we set the DMA address to 0, and then we do free pages, RX info page. And I think the page order is just 0. All right, and then SKB. Well, we don't have a page. We don't have an SKB. We do have a page. All right, so we set the page is equal to null. All right, and I think that's what we need to do here. Oh, and I should actually add a test here. If not RX, oops, if not RX info page, then we're going to return. Okay, cool. Just to make sure that looks good. All right, so that is the free descriptor and the free buffer. Okay, great. Now I need to do a prepare RX descriptor. And the idea with this one is this will set up the RX descriptor for in the ring to be ready for the receive operation. And I guess this is sort of handled by the TX code here, the TX, not the TXCQ, but the actual start transmit function. So, some of this stuff has to be kind of grafted together here. Okay, so this is going to be pair RX descriptor. All right, so we have the dev, we have the info index. Right. Okay, so this one is okay. I need the RX descriptor as well. See here. So this is going to be coming from. I thought I had something for the descriptor. Okay, there's the descriptor. I got the TX. I got the info ring. I got the descriptor. Oh, all right. See you later, Houston. All right, turn off the cat cam. Okay. Great. So I have the device, I have the RX info ring, I have the RX descriptor. This is going to be equal to, let me see here. Well, let me go ahead and pull this from, where was this? Here we go. Let me go ahead and put this in here, free RX descriptor. This is actually not where this is going. Going here. All right. So Rx descriptor equals, this is the RxQ region, right? Plus index times 16. And then page equals RxInfo page. Okay, great. Page order, that's fine. Len, wait a second. So where do the page order values get set? That's actually what I'm trying to figure out right now. So this free Rx descriptor, I'm forgetting where that gets set. Oh, does that get preloaded into the Rx ring? Okay, how does this work again here? This is so it creates the ring, it sets the page order, but oh. Ring page order. Got it. Okay, got it. Okay. So I have the page, U32 len equals page size. Okay, great. DMA ADDR, ADDRT, DMA ADDR. So we need the DMA address. So this is prepare Rx descriptor. Okay, great. So, okay. Maybe I don't need to do this quite yet here. All right. Alrighty then. So let me think here. I'm going to do page equals dev alloc pages. Where was this? Oh, page order. Well, page order is 0. All right, great. If unlikely not page. Let's see. Fail to allocate page here. All right, and then I'm going to turn enomem. All right, great. And then I map the page. DMA ADDR equals DMA map page, and this is going to be no, yeah. Wait a second. All right, this is dev. Yes. Page, right? And 0 len DMA from device. Okay, great. And then there's the possibility for a mapping error, so I'm going to copy that from TX here. If there's a mapping error, then we got to do something about that. Yeah, it's a mapping error with the DMA address. Then we go netdev error, and what do we do about that then? I'll return -1, and then we got to do 3 pages, page 0. All right, great. Then we write the descriptor. Same thing as in the TX direction here, both the descriptor and the info page. Right, so we got the TX descriptor and the TX info page, except it's going to be RX. Okay, RX, everything. There we go. So we have the length, we have the address, we have the, well, there's no SKB, but there's a page, so let me fix that. Page, there's the length, there's DMA address. Okay. All right. I think we're doing pretty well here. And then I do return 0. Okay, excellent. All right. Then mqnic. All right. So then I need to do refill Rx buffers. Yes. All right. So this is going to be. Let me see here. Refill Rx buffers. Struct, and this is cndm priv. Okay, excellent. So we have that, and then we do u32 missing. Missing equals 256. I'll do 128 actually, minus the priv rxq prod minus priv rxq cons. All right, great. Int ret 0. Actually, take a look at the message output from here. Has this looped? The 213, has it looped yet? I don't think it's looped yet. No, it has not looped yet. Getting close. All right, where was I? Ret equals 0. All right, so if missing is less than 8, I will return 0. We're gonna do this in batches. So 4 minus is greater than 0. Okay. Ret equals cndm prepare rx descriptor, and this is going to be priv and okay, so this is then priv prod rxq prod and ff. All right, need to fix that, but whatever. All right, if ret, then I will break. All right, and then priv txq prod plus plus. Oh, this is rxq, not txq. Oh, that could be bad. All right, and then we enqueue it. DMA, WMB. All right, and then I need to return ret. Then over here, I need to write that pointer, right? So, writing the producer pointer on the RxQ is this one. Yes. All right. So I write the pointer, and yeah, okay. Then we should be ready to start firing off receive operations, I think. Okay. So there's 2 more things I need to do, right? Well, several more than 2 more things, right? So one thing that I need to do is I need to make sure that I am cleaning the RX ring here. So this is going to be the RX buffer. Okay. And actually, I need to make sure that all of these pointers get set early. So I'm going to go ahead and move them all up, make sure everybody's happy. Yeah, that's kind of important, because if these pointers are not set correctly when any of the cleanup code runs, then we have a problem. All right, so I'll put all these up here. Okay, there's the pointers. That's going to look pretty good, I think. Okay. Great. DQ consumer pointer process ring update consumer pointer replenish buffers. All right. So with this one here, we're freeing the RX buffer. That looks good. At what point do we need to set this thing up? I think we're going to fill it when we open it. So up here somewhere after, yeah, okay. So up here somewhere we have to go ahead and preload the buffers for RX. Where is this going to go? So I need to call refill RX buffers for that. Let me see where exactly that needs to be called in the process of setting everything up. Okay, update interaction table, configured scheduler, flow control. Where does it call the buffer filling step? Open. Oh, I guess this is maybe it's called during open RX spring. Okay, got it. All right, so after open RX spring, then it goes ahead and calls all that. All right. Maybe I'll do this first. Okay. So refill RX buffers, that needs to be, I think, included in the header file. And then we'll go ahead and we'll do a test build on that, won't we? Oops. Is that going to build? Oops, bunch of errors. All right, great. So first one is line 212. I have an extra argument, so I will remove that. That looks good. All right, rebuild that. $234. Prepare RX descriptor. Oh, I think prepare RX descriptor should actually be returning an int. Yeah. Okay, ndev is not declared, so I need to locate that. Wait. Where did I need the ndev? Oh, was that for? Okay, 240. Okay, wait, what? Go to 42. Oh, this should be returned. Okay. Always important to make sure that this thing compiles early before syncing it around, right? Okay. So this did wrap and it seems to be working, right? So this got up to 255 and now back to 0. So, so far seems to be doing what it's supposed to do. That's excellent. All right. Let's try the new module then and see what happens. Why did this start at 0 then? Something is not making sense here. So this called a bunch of free descriptors, but why did that happen? Let me take a look at that and see if I can figure out what happened here. So this should be called with the free TX buffer, right? So index starting with the TXQ consumer and working its way around the ring. TXQ consumer pointer should also be getting updated by this. TXQ consumer is getting set to consumer pointer. So I grab it and then I put it back. That does not make a lot of sense here. Oh. No, something did break. I don't know exactly what, but... Oh, I see. Yeah, this stopped processing stuff after it looped, so that means I must have a problem with the, this thing. Well, alright, I got stuff that needs to be fixed, but, you know, it is at least partially working, so we can send 256 packets before it, before it dies. And let's see about this here. Okay, so we prepared 128 RX descriptors. That's useful, I suppose. Okay, well, that's at least a start. Let me go ahead and RM mod that, and okay, so we freed all the RX descriptors, and there were no TX descriptors to free, so that's pretty good. Yeah, alright, so there's something wrong eventually with the phase tag handling somewhere, so I'll have to figure out what happened with that. But, okay, one step at a time. One step at a time. Right. Where was I here? We're still working on the RX path, and what is the next step here? So I have it filling. Now the next thing I need to do is to get all of the setup done for being able to actually pull the TX ring. So if we look at the for pulling the RX ring, sorry, pulling the TX ring, right? We have pull TX CQ and we have process TX CQ. So I'm going to go ahead and copy these two for now, and I'm going to go down to the bottom here because we got to do the same sort of thing here. We're going to pull. All right, so I'm going to go through and I'm going to rename all TX to RX because that's going to be, whoops. These are all going to be done with RX. Okay. Okay, so this is going to be for that. All right. I'm going to go ahead and comment this out for now. Oops. Yeah. Oh, I did that. Is that what I did? Is that what I did? Somehow I turned off the numbering, and I can't remember how to turn that back on. Oh, there we go. It's semicolon. All right. Always annoying when you hit some random key and you're not sure what exactly you did. Okay, so CQ consumer index. I can't remember if we're doing this exactly the same way as before, but anyway, that's fine. We're going to start with this. We're going to go back up to main here, so we need that, right? That's going to be for the nappy function, or the, yeah. Then I go up here, we're going to add this, right? We're going to add this, right? I'm going to go over to here. I'm going to go ahead and add the pull RX CQ. All right, so we have TX descriptor, TX CQ. All right, so this is looking pretty good. Anything else I need to do down here? I think this is all. I think this is all ready to go. So all I need to do now is I need to set up. Yeah, so all I need to do is finish implementing this one routine, and then I think we're good to go. Maybe, hopefully. I'm not 100% sure. We'll find out. Yeah, okay. So this one I think has a lot of similarities to what we already did. So I have that. These are going to be, yep, RxCQ. Yep, that's going to be good. While less than the budget. Yep, that all looks good. Whoops. I do that. All right, I do that. I do CQ index. I pull that. The completion, I pull that. Phase tag, we pull that. DMA RMB, we pull that. Okay, but we're not simply freeing the descriptor. So, well, or I think I do that at the end, right? No. What do I do? All right, well, we'll figure this out here, right? So I do that. Okay, so now I need to start doing some more complicated stuff here. So I have the index. Now I do RX info. Right, so I need RX info and RX ring. Let me see. It's actually going to be somewhat similar to the free RX descriptor, where we're going to need a lot of the same information. So I'm going to go ahead and copy that for now. And I'm going to go ahead and paste this here, and then some of the stuff will need to get moved around. Okay, well, actually, I need to define that up at the top. Okay, there's the RX info, and then we need the descriptor. That is going to be the RX, that is going to be descriptor. Okay, great. So I have that. Process RX descriptor index. Yep. Okay, if all right. All right, let's see here. Okay, well, actually, this is a good check to have, because if actually, so RX to, okay, yeah. So if that's null, then we have a problem. Okay. Now what do we do? Epi get frags. Okay. skb equals snappy get frags. Let's see, then I do, what is this, priv rx snappy. Okay, and I also need to define that skb somewhere. Let me see if I have an skb definition I can just copy. Right, I can just copy that. Why not? Okay, cool. Process rxcq, so there we go, there's our skb. Okay, great. So we have the skb. So we do nappy get frags. If that fails, what does this mean here? So if skb, if not skb, one moment here. All right, yeah, it looks like I might actually have a hard stop here. I will spend just a couple more minutes on this and see if I can get enough of this. This is like so close to being complete, you know, this might actually be achievable. So let me see what we got here. Right, so we got to check to see. All right, so we got to get the skb for the get frag, so that looks good. Timestamp, we can skip that. Record RxQ, who cares? Okay, all right, so we got to unmap a page. We got to unmap a page, set the DMA address, and this to null. Okay, so now what we need to do is skb fill page desk. I need one underscore here, right? And then this is going to be skb 0 page rx info. Oh, I think page offset is 0, right? And then length. Okay, great. Yeah. Okay. I think that's what we want here. Rx info. Oh, all right. So the page I'd already set to null. Oh, had I already pulled out the page? That's a good question here. I did not pull out the page. Okay, I see. So I need to create another struct page up here. Struct page. Okay, there we go. So the page, I will do page equals rx info page. Okay, and then this is looking at not page. Okay, page there. Set that to null. I have the oh, I don't need the free pages. That would be bad if I screw that up. Okay, great. So we do that. We set page equal to null. All right, let me see. So I have the page, and then I do skb sh info skb. I want to set the number of frags equal to 1. skb len. This needs to set to length. All right. So where do I get len from? All right. So len. I need another u32 len. Len is going to be coming from, where is the rxinfo len? Okay, where's the completion? Okay, I have the completion. All right, so len equals min t u32 le 16 u cpl len, and then this is going to be rx info len. All right, great. That looks good. That sets the length. I do the skb len, skb data len, skb data len, set to len, skb true size equals rx info len. All right, great. And then we hand off the skb happy gro frags. There we go. Okay, and then I need to specify that the rx snappy here. Okay, great. So I do that. Okay. And then is that it? Oh, I think there's still more that I need to do with this. Okay, so I do that. Okay, done. CQ cons, increment all of that. Shoot the new index at the top. That looks good. All right, so that looks good. All right, there was a piece of this that was confusing me, but that seems fine. All right, so I do all that, and then at the bottom, I need to do refill rx buffers priv. Right, so I got to do that, and I think that's basically it. All right. Oof, moment of truth. If this works, we're done. If this crashes, it crashes. And then I think I have a hard stop here, so I probably have a typo I need to fix. Yeah, I have some typos. All right. Okay. Is this all right? NetIF nappy add. Okay, that I have a mistake here. Where is this when it's when I'm opening up the rings? When I set up the nappy. Okay, so for RX it's just netif nappy add, not okay. Netif nappy add. Okay. Okay, dev undeclared 323. 323 dev. All right. Okay. Okay. Well, let's see if this does anything useful. Okay. Let me make sure we did enable that. Okay, interesting. All right then. Okay, let me see. So we have this. Not doing much. Well, I guess there's no traffic right now. All right, so. Okay, IP ADR add 10.0.0.1 for dev. Okay, and over here I'm going to do IP ADDR add 10.0.0.2 24 dev. Okay. Oh. Yeah, something is still not quite working right. I'm not sure what it is. Oops, I didn't want to kill that. Alright, so it doesn't seem to be crashing, but at the same time, it doesn't seem to be working. Well, free RX desk. That's interesting. Seems to... Oh boy. Okay, yeah, I screwed something up in here somewhere. Alright, well, I got some work to do. So I have a hard stop now, I gotta shut this down, but, we got at least the transmit path working, the receive is almost there. It's just gonna need a few more cycles probably to get the kinks worked out, and I think I might have known what I screwed up here when I'm unloading the driver. I'm not disabling the queues in the hardware. So yeah, that's a big problem. I'll have to fix that, and then we'll have to revisit this later. Well, thank you very much for tuning in anyway. I'm going to go ahead and shut this down for the time being. And yeah, have a nice rest of the day.